Hello everyone. This is Jian Kang Deng from Imperial College London. Welcome to today's workshop. Today's topic is face biometrics under COVID. This workshop is jointly organized by Imperial College, Tsinghua University, and Insight Face. Before the workshop, we have organized a mask face recognition challenge. Today's agenda, including the following 5 parts: the opening remarks, introducing our training data and the test benchmarks of our challenge, and then 4 invited talks from academia and the industry. After that, there are 5 reports of the top-ranked solutions. Afterwards, there are 2 reports of workshop papers. Finally, there will be a award section. During the COVID coronavirus epidemic, almost everyone wears a facial mask, which poses a huge challenge to face recognition. To cope with the challenge arising from wearing masks, it is crucial to improve the existing face recognition approaches. In this workshop, we have organized the mask face recognition challenge and focused on benchmarking the face recognition methods under the existence of facial masks. We have 2 main tracks. The first track is insert face tracks, and the second track is web face track. So for the insert face track, we have 3 different training data. The first one is Microsoft 1 million. The second one is Gilint 360K. And the third is unconstrained track. And for our test data, we have masked test set, children test set, and multiracial test set. For the masked test set, we evaluated the accuracy between masked and non-masked faces. For the children test set, we tested the evaluation accuracy among children between 2 to 16 years old. For the multiracial test set, we evaluated the accuracy on global multiracial races for such as African, Caucasian, and South Asian, East Asian. And we ensure that there is no overlap between the public training data and our test set, because our test set is collected from non-celebrities. For the masked set, TIR is measured on mask to non-mask 1-to-1 protocol with FAR less than -4, E-4. For the children set, TIR is measured on 1-to-1 protocol with FAR less than E-4. For the multiracial test set, the evaluation, the TR is reported at FAR equals to E-6. So in this insert face track, we use the weighted FAR to rank the result. 25% of result TR is weighted to mask the test set, and 75% is given to multiracial test set. And here is a visualization of our test data. And we intentionally decrease the quality of the exemplar facial image to ensure data privacy. On our test server, all of those test images are still in high quality. And here we give the baseline results. As we can see, for the public tested dataset FW, CFP, HDB, and IGBC, there is a small performance gap, but on our test data, the performance gap is more obvious. By using the mask augmentation, we can see that there is a huge performance improvement on the mask track. For the Microsoft 1 million track, we set the inference time below 10 milliseconds and the feature dimension below 512, and the mask data augmentation is allowed. Participants need to submit the ONX model and get the evaluation result from our online server, and all of the test images are invisible during the challenge. There are 136 teams with more than 4,000 model submissions to the Microsoft 1 million track. For the Glint 306K track, there are 86 teams with more than 3,000 model submissions. Here, the inference time is increased to 20 milliseconds, and the feature dimension is increased to 1024. For the unconstrained track, there are 74 teams with more than 1,500 model submissions. We do not have any constraint on the model size, inference time, and also the feature dimension. Here we show the top ranked solutions. For the interface Microsoft 1 million track, the first place is obtained by SenseTime Research General Model, SenseTime SCG STC group. And the second place is BOE AIoT CTO. And the third place is Alibaba Damo Academia. For the interface track, interface Glint 360K track, the first place is achieved by SenseTime Group Limit, best model group. And the second place is obtained by SenseTime Research General Model, SenseTime SCG STC. The third place is Microsoft Research Asia. For the interface unconstrained track, the first place is SenseTime Group Limited, best model group. The second place is Alibaba Damo Academy and National University of Singapore. And the third place is TopPen. For the WebFace track, we employ the largest public dataset named WebFace, which includes 2 million identities and 42 million images. For the tested data, we have the controlled images and word images. And for the controlled image, we target to evaluate ID photos such as visa and driving license. Controlled face in our test set is defined as near frontal, normal expression, not in low resolution, high resolution. For the word image, those images are collected in unconstrained scenarios, including large pose, partial occluding, resolution variation, and illumination variation. So in the WebFace track, our the different algorithms are measured on force non-match rate, which is defined. Sorry.
登健康码这个应该是不是
？So please mute yourself. Check. Okay. Okay. So for the evaluation metric in the web fast track, we employ the force non-match rate, which is defined as the proportion of matched comparisons below a threshold set to achieve the force match rate specified. FMR is the proportion of imposter comparisons at or above that threshold. It is worth noting that noting that low FMR at the same FMR is better. So we care about FMR at FMR equals to 10 to minus 5. So in the web fast track, the total time on the CPU is set less than 1,000 milliseconds. This time includes the face detection alignment and the face feature embedding. Here we show some visualization of our test data, and all of our test data are from celebrities, and we manually remove the overlaps between our test data and our training data. So for the web fast track, we have more than 80 teams and more than 1,500 model submissions. And the top ranked teams are SenseTime Group Limited, Best Models Group. And the second place is Face Group David AI Lab, Kakao Enterprise. And the third place is Alibaba Damo Academy, National University of Singapore. For the WebFest FR track, there is no masking in this track. The first place is Alibaba Damo Academy, National University of Singapore. The second place is Nanyang Technological University, Zhejiang University, National University of Singapore, Institute of Automation, Chinese Academy of Shenzhen Technology University. And another second place is Topeng. The third place is Shenzhen DeepCam Information Technology, Link Technology USA, Link Spirit Technology USA. So yeah, this is our first invited talks from Patrick Cruiser, and Patrick is a research scientist at NIST. He evaluated all of the NIST submissions, and FRVT is the most well-known benchmarks in face recognition, and he has a lot of experience in or deep insight on this face benchmarks. So welcome to Patrick to give us a presentation on the NIST FRVT benchmark, past, present, and future. Hi.
Okay. Yep. Thank you, Jiankang. Yeah. Hi, everyone. Should I share? I go.
Yes. Let me stop my share.
Okay. Can you see that?
Yes, I can see.
Okay, so yeah, thank you for the invitation. I'm glad to be here. It's a good workshop agenda today, so an extremely impressive competition that you put together there. We do things a little bit differently, and you will see how coming up. So I work for a US government lab just outside Washington, DC, and we run a small team on currently 4 different face recognition benchmarks. One-to-one, which is simple comparison. Also one-to-many, which can be multiple comparisons with a sort operation, or it could be some fast search data structure, some engineering that goes on with that, and that's a bigger sort of marketplace segment. Morph detection, which is a particular attack on face recognition, and then can we look at an image and say if it's a good image or not? So automated quality assessment. So these 4 benchmarks are open permanently, and anybody worldwide can send us an algorithm behind our API, and we run it, and we do that, and we publish the results. So the results appear on web pages, but also in reports, and you can see these listed. Currently, there are 7 reports. One-to-one performance, accuracy, speed. One-to-many, the same. Part 3 is about demographic effects. I'll talk about that later. Part 4 is on how well you can find a morph, combined face image. Part 5 is about can you look at images and say whether they will match. So that's image quality. Part 6 is face masks. And part 7 is about one-to-many in small galleries for the travel industry, future travel without boarding passes. Yeah, so I said NIST is a little bit different. We run our benchmarks and we have data, image data, maybe 200 million images from about maybe 70 million people. And we form galleries up to say 12 million people for one-to-many search. And we run all various benchmarks, and the images are coming from operations, typically United States government operations, so immigration, border crossing, criminal justice, and some others. And this data is truly sequestered, so no developers have access to this data. You can't train on the test data. You can't tune hyperparameters on the test data. And we limit participation in these benchmarks to every 4 months. And that is done to deliberately slow down sort of repetitive testing to just tune the algorithms or tune the models in some way. And so we deny access to the data. You don't get to see the images, and you don't get to train on the images. About the organization, as I said, we're an independent lab. We don't regulate face recognition. So we are not making rules for the use of face recognition. We don't make policy. And we do all of our benchmarks for free. So this gives us independence. We don't take money. We publish the results with the developer names, and we make some efforts to make sure that the participation is not anonymous. And so that implies a reputational risk for developers, that if they send us software, their results will be public. We're not developers, we don't build algorithms, so we are not really competing. And we don't see code. We do everything as a black box behind a C++ API. Python is possible also. And we don't certify, right? So what do we report? Accuracy, one-to-one, the 2 error rates, false non-match, false match. We also report the stability of those across demographics and across image types. For one-to-many, the names change, but again, 2 types of error rate, false positive, false negative. And for false negatives, we split it out into sort of 2 application-based focuses. So one is to just plot rank-based accuracy, the false negative identification rate as a function of rank for investigators, but also a threshold-based value for those applications where you sort of want the system to make a decision in real time. And that's a fairly big topic. You don't often see threshold-based metrics for identification appear in the academic literature. They probably should. For resources, we plot all the durations of sort of all the processing steps. So inference, detection, combined. one-to-one comparison, one-to-many search. Particularly, we note if an algorithm is giving you sublinear search, and how long does that take to prepare, say, a KD tree or some kind of index or dictionary. What's the embedding size, the template size, what's the model size, how big is the code, and how much space is it using at runtime in memory. That turns out to be important for different individuals, different applications. So here's some toy examples of data. So some of it is quite highly cooperative, and some of it is less cooperative. Recently, we've added the images at the bottom left, kiosk ATM kind of images. We also do a benchmark of profile view images, wild obviously also, and some others where the image quality is definitely not what you want if you can control it. So yeah. And then this is our sort of a performance leaderboard. So a whole lot of numbers. They are false negative identification rates from one-to-many search algorithms configured with a threshold to give us a false positive identification rate of 1 in 333. So false positives would be rare. Most searches would not return anything when the person is not in the gallery. That's a metric, again, that doesn't appear in the academic literature very much in one-to-many, but it's important operationally. So box B, we name the algorithm. Box C is a hyperlink to a report card, algorithm-specific data. D is the date that it was submitted. Column E, what's in the gallery, E1, what's in the probe set, E2, how big is the gallery, E3, and then the results of these false negative rates, E4. We do this, and that column there, E4, is this 90-degree yaw angle, so very difficult recognition. And you can see, I think the best algorithm there is CloudWalk, 11% miss rate, 11% false negative identification rate. Some algorithms are just not even attempting to do this kind of recognition across 90 degrees of pose, and error rates are essentially 100%. Mugshots are easier in column F, a gallery of size 12 million. That's very good images. Typically, on the right side, we have 2 columns for aging, and maybe our standard benchmark is column G, which is now quite a challenging set. The lowest error rate recently yet is from a Korean company, about 7% false negative identification rate in a 1.6 million size gallery. So we do this with masks. Also, at the beginning of COVID, we started with digitally applied face masks, and we maintain this table on our webpage. And you can see, I think SenseTime is the most competitive algorithm recently. It's giving something like a factor of 7 or 8 times more false negatives than on the same set of photographs without a mask. So, you know, there are these increases in recognition error rates, but these algorithms now are probably viable operationally. At the beginning of the pandemic, when we started using pre-pandemic algorithms, they weren't good enough generally. The final column is whether the false match rate actually goes up because you put a mask on the face. And in most cases, the false match rate goes down, but there are some algorithms that become less secure because the false match rate goes up. So that's sort of important to keep track of as well. We plot trade-offs. Here you can see the accuracy on the vertical axis. You can see speed on the horizontal axis. And you can see there's this sort of trade-off between very fast algorithms and algorithms that take more time to do to run the model. We have a hard limit of 1.5 seconds in our tests, just because we want to complete the tests quite quickly. All of our tests run on CPUs, which are used generally in operations. We don't use GPUs mostly. So there's a big topic in face recognition. If you read the press every day, there is talk of demographics and this problem of bias. And so obviously this is just a toy plot, but there's a trade-off between false negative and false positive. And in this case, for demographic number one, older white men, Caucasian men, and a second demographic, say, we choose as younger Asian females. And maybe the accuracy is higher or lower or something like this, but you see these two curves and they're separated like this. Now it is conventional, it's very common to report accuracy for those two demographics by finding the false match rate of, say, 1 in 1,000 or 1 in 100,000, and we compute two numbers, say 3% and 5%, and we tabulate those and we say that the accuracy on young Asian females is worse than it is on older white guys. But this is actually the wrong way to do this, because systems are configured with fixed thresholds. So if you walk through an airport, people from all sorts of demographics will use that system, and typically the system is configured with one threshold. So here we've set the threshold to pi, and at that threshold there is both a change in false negative rate across demographics and a change in false match rate across demographics. And it turns out that these changes in false match rate are, they can be 1 or 2 orders of magnitude. And I will show you that on the next slide. And the change in false non-match rate is typically a factor of 2, a factor of 3, maybe a factor of 4. It's much smaller because algorithms are very accurate. But the false match rates change even with very good images. So this is comparison of very good immigration photos, and along the top, men, along the bottom, women. Each tile is encoding a false match rate for comparison of images of different people. So at the top left, we see that this algorithm, which is from Imperial College a couple of years ago, gives us a false match rate on young white men, 35 to 50, of 1 in 30,000. And that's the log to the base 10 of that false match rate. But on the other side, if we look at a Chinese population, female, over the age of 65, we see false match rates are 3 orders of magnitude higher. And that is quite a big effect, 3 orders of magnitude on it's quite a narrow demographic, but that effect is there. And this is a false match rate. So we fixed the threshold and we've computed false match rates for these various age groups and sexes and countries of birth. What's actually happening is that the imposter distributions, and this applies for many algorithms, not just Imperial, but the imposter distributions are not stable. They move depending on the demographic group. And that is unwelcome. If you make an analogy with cryptography, we don't want a 64-bit key being used for one population and a 12-bit key being used for another population. And this matters particularly in one-to-many identification systems. Less so in a one-to-one system, but if this algorithm was used in a one-to-many identification system, we would see much higher false match rates on, say, elderly Chinese women. This is a Russian algorithm, perhaps one of the most accurate algorithms that we've tested from Vision Labs. And we see, in this case, the highest false match rate there is on elderly Nigerian women. And this, again, is much higher than in white males on the left side. If we go to a Chinese algorithm from CloudWalk from a year ago, you can see that the country labels now have changed. And the lowest false match rates are on Chinese faces from men. And the highest false match rates now, again, maybe 2 orders of magnitude higher, are on faces from India. So this demographics issue is important, and algorithms, I think, need to make some progress in stabilizing imposter distributions and stabilizing genuine distributions so that the false negative rates are also stable across demographics. So we will shortly introduce some measures of this, and one way to do this, one possible way to do this, is the first line there is to look at the worst demographic false match rate over the best demographic false match rate, which is what I just showed you. And you compute a number, and you do that for both false match rate and false non-match, and then you combine the two into a statement of inequity. This follows a paper coming from the IDIAP lab in Switzerland, which did a slightly different formulation, and we think this one is better. But yeah, so that's one way to do it, and maybe we will make it an equity measure instead of an inequity measure. But right now, high inequity would be a bad thing. A different way to do this that was suggested by colleagues at Amazon is to look at the variability of the error rates around the geometric mean of the error rates. So you can see if we take logs that you've just got these ratios and we sum them up, but the absolute value. So it's a variability measure. And that's a different way to do it. And because it's a geometric mean, this is less sensitive to very large values in these FMR and FNMR estimates. So we will start reporting that and ask for a comment from the academic and industry community on whether these measures are good or not. Twins, we will issue a report on twins recently. Twins have long been thought to be a difficult problem for face recognition because they can give false positives. Twins are quite common in the United States. In 2015, actually 2019, we are looking at about 3% of all babies in the world are twins. More rarely, they are identical twins. More commonly, they are fraternal twins. And those rates vary quite considerably worldwide. So twins are less common in East Asia, more common in West Africa, for example. But twins are becoming more common because of changes in the way people have babies. So this is a sort of an operational problem because twins give false matches. So here we use 3 different algorithms in a one-to-many mode. We put 1.6 million photos in a gallery, and we put twin A in the gallery. We searched with twin B. And of course, these 3 algorithms gave quite high scores, and the twin was returned at the rank 1 candidate position. So we get these false positives with high scores. And if you were a criminal investigator, you would need to try and figure out, is it a twin or not? This happens also with fraternal twins, but the scores are lower. One algorithm gave the twin at rank 11, but usually they are at rank 1. When they are the same sex, you can have different sex twins. Now, a possible solution to this is to have more information, and more information that is not genetically linked. So it's not phenotypic. And skin texture is known to be in this category. And if you've got this sufficient resolution, then you could look at skin texture and correctly disambiguate twins. This was done by a French company in 2004. There's a patent that is listed there for their method, but it's handcrafted features, slow comparison time, and it requires high resolution. And as you will know, most models that are being used in recognition tests today are using lower resolution images. So this texture is perhaps not visible. So a future challenge would be to discover perhaps deep convolutional networks that can look for skin texture. If that was possible, then we would see twins separated, but we would also see some of the false match rate variations in demographics be reduced. So that is a sort of a challenge for researchers, but it depends, I think, on high resolution imagery. So what is the future for the FRVT benchmark? We will add 2 more benchmarks. So in the center of the slide there, we will add a benchmark on image quality assessment, specifically looking for particular problems with images and can we automatically assess those. We will also add an ongoing benchmark on presentation attack detection. So software only solutions, you would look at an image and you would say there is something nefarious about the image. This is an attack image or not. Obviously, we will plot the 2 error rates, false positive and false negative. And we will, at the bottom of this slide, we will add a report on twins. We will also add another report on demographic summaries, which I showed you earlier. So that is what is coming up. The other benchmarks will stay the same. We update reports from these benchmarks with various frequencies. The one-to-one and one-to-many reports are updated about every month. And another one we hope will be released in the coming week. So image quality, just a few comments on image quality. Image quality is better when you have subject cooperation. Image quality tends to be much worse when you just use a camera and the subject is not making a cooperative presentation. Quality exists on essentially an open-ended spectrum up until the point where we have no signal whatsoever. And face recognition algorithms are used increasingly with poor quality photos. So a new benchmark that we will establish wants to look at software and assess its capability for looking at single photos and saying, are there multiple people? Are there no people? Is the image frontal to the camera? What is the yaw angle or the pitch angle? Is it misfocused? Is it noisy? Is it cropped? Is it overexposed? And are there illumination problems? So some other measures too, we will release a test plan for that within the next month. Ahead of a quality conference that we are running virtually with colleagues in Europe. And this is important for big identity management programs for ID credentials and border crossing. Can you look at images and know whether you've got a good image? And so that is the sort of the topic of the conference. We've got speakers from industry and government and academia that have looked at this problem and in a few cases written software to actually produce algorithms that will do automated image quality assessment. So that is coming up. And that is the team that implements FRVT today. Thanks for paying attention. You can email us at that address. I'm happy to answer questions now or offline. Thank you.
So, thanks for your talk. So we have collected some questions from the audience. The first one is, there is also mask face recognition in the FRVT, but the mask face is simulated. And is there any bias among simulated and real mask evaluation? And is there any plan to test masked face recognition with real world faces with mask?
Yeah, we have some small data sets. Obviously, it's difficult to get a big data set with lots of masks. I know various organizations have done that, but we are not going to push this much further. I don't think, well, hopefully the pandemic ends and hopefully we don't have to do masks all the time. So how important the problem is, I think we would prefer to work on other things like PAD and quality assessment.
Okay, thanks for your answer. So the second question is, the lead board of NIST FRVT is dominated by companies. I know this challenge is for vendor test, but is there any chance for academia lab to get a good rank? Do you have any suggestions or some?
So the answer to that is yes. There is an opportunity, and the opportunity, the person who knows a lot about this is sitting in front of us now, Jian Kang, and you and your colleagues from Imperial gave us the ArcFace algorithm maybe 2 years ago or 3 years ago, and it performed at the time. It was maybe, I think, top 5 or top 10 algorithms. Since then, we have InsightFace, which remains a very competitive algorithm. The algorithm is fast. It has a C++ interface, and academics can do this. You know, it's the barrier to entry is some software engineering, but it is possible. We are not going to run MATLAB unless it is quick and it's behind a C++ API.
Okay, thanks for your answer. The third question is about the accuracy of different races. Is the training data matters or the algorithms can do the debiasing? What's your opinion? So some company can collect the multi-racial data, but it's not the same case for all the company, but some other company can only get biased data, and they can only design the algorithm to improve the to do debiasing. So what's your opinion on this? Is debiasing can complete by algorithms, or it can only complete by data?
So I think we have seen cases recently of different developers making algorithmic steps to address this issue. I think you can train the data, you can train with weighted data sets, reweighting, you could change the cost functions. I think the false match rates maybe need to be treated differently than false negative rates. False non-match rates vary a little bit. They are subject to bad photography. So if you have very poor illumination, you can see false negatives on, say, dark-skinned individuals, or overexposed photos on very pale-skinned individuals. But the false match rate instability is a problem, and a company in Europe has made some public presentation on this. It's the OnFido company. I think an organization in the USA talked about this also recently at a conference, TrueFace AI. Yeah, I think it's an algorithm solution can get us a long way here.
Okay. Thanks for your explanation. The last question is, do you think the scores are still discriminated after the top 1-to-1 submission reaches 1990.7? So currently, on the FRT lead board, and the performance gap is very small. And do you think there are still enough space for us to improve?
Yeah, so I was asked that question 2 years ago, and you know, the error, the false non-match rate then was, say, 0.8%. And okay, there were many developers near the top, you know, SenseTime, CloudWalk, NEC, IDEMIA, you know, the usual corporate developers, very competitive. And since then, the error rates have come down by maybe a factor of 3 or factor of 4, depending on which kind of data that we look at. And fixed databases, reduced error rates, progress is being made. The algorithms today are more tolerant of bad quality than they used to be. We have the ATM, telemachine, kiosk benchmark in one-to-many. You will see that soon in one-to-one. And the error rates there are 5, 6, 7%. So there's a long way to go. We don't like to report TAR. We like to report 1 minus this. So FNMR on a log scale. And so you can see accuracy reduce, error rates reduce on this log scale. We divide by 2, we divide by 2, we divide by 2. Yeah.
Okay. Thanks for your answer. So yeah, is there any question? Is there any other online questions to Patrick?
There's one in the chat.
One in the chat. Okay, it's from Cargo Enterprise. We know one-to-one verification is constrained about 1.5 second in interface, but 1 minus n, 1-to-n protocol is still limited to 1.0 second. Is there any chance to is there any change plan in the 1-to-n protocol in the future? So about the inference time.
Yeah. So yeah, we understand this issue. The short answer is no. We don't plan to change it. We have recently, in one-to-one, this is a result that's not published yet, but we saw a very famous biometrics company send us an algorithm at 1.4 seconds. So just under the limit of 1.5 seconds. And obviously they could not send us the same algorithm for one-to-many. We believe that many applications require quick response time. So that's why those limits are in place. If I see who's asking the question, if you really want the change, then send us an email and tell us why you want the change, and maybe we will change.
Okay, thanks for your answer. Is there any other question? If there are any other online question, if there is no formal question, thanks for Patrick. Thanks for your detailed introduction of FRDBT benchmark. Thanks for your answer to those questions. Thanks a lot.
Thank you for the invitation.
There are another message. Okay, thanks for the. Okay. Next talk is from Xiaoming Liu. However, it is a 10 minutes before the present agenda. So, Xiaoming Liu, are you there? No. Let me. Professor Xiaoming is online. So the second talk is trustworthy face recognition from Professor Xiaoming Liu. Xiaoming Liu is MSU Foundation professor at the Department of Computer Science and Engineering of Michigan State University. Yeah, he has been the area chair for numerous conferences, including CPR, ICCV, ECCV, ICR, NIPS, and he has authored more than 150 scientific publications and has filed 29 US patents. He's a fellow of ARPR. So welcome to Xiaoming Liu's talk today.
Hello, good morning, Jiankang. I saw according to the schedule, my talk will be started at 8 a.m., right?
Yes, because we ran the 10-minute QA section, but sometimes the question is longer or shorter. So
Okay, no problem.
Yeah, we can start now. So you have more time for your talk and more time to answer the questions too.
Sure. The only thing that my video camera seems is not enabled. I need to reboot. Should I reboot my machine to enable my video, or you think this is okay?
Okay, so it's both okay for us if you.
Yeah, maybe it's better. Let me restart my computer. Take 2-3 minutes, then I can start my talk. Yeah.
Okay.
Yeah. Okay, let me do that. Yeah, sorry about that. Okay, let me open my slides. Okay, could you see my slides?
Yes, we can see your slides.
Okay, let me make it full screen. Okay, are you seeing the small one or you see the full screen right now?
Caption version maybe,
Okay.
not the full screen. Yeah, now it is full screen.
Okay, good. So should I get started?
Yes, yes.
All right. Yeah. Okay. Good morning, everyone. Well, good afternoon. I think right now is in China time. It's local time. Yeah. Thanks, Jiankang, for the introduction as well as the invitation for the talk. So today I'd like to share some of our research in trustworthy biometrics, especially face recognition. And so this has been joint work with a few colleagues as well as my students. And so we all know that biometrics, especially face recognition, has been widely used in a lot of applications, right? So airport, checkpoint, and you go to shopping in sort of Amazon Go, and as well as entries to sort of different buildings. So as we all know, biometric research has been focused on improving the classification performance, because mostly we want to recognize individuals based on their behavior as well as sort of biological characteristics. And previous research on biometrics focus on the accuracy improvement on different modalities, including face and fingerprint as well as iris. However, as a biometric is being used in more and more application scenarios, there's also an increasing amount of society concerns regarding the technologies. And for example, there has been research, trying to study that the fingerprint sensor on your phone is not necessarily safe. It could be attacked using things like sort of mask print. And also, for face recognition, there has always been a sort of concerns regarding whether it is biased, toward different demographic group, right? So this was one case for a gentleman in Detroit. He was taken into the police department because of his face was matching with a sort of surveillance videos, but in fact he's not actually the people who did the crime. Okay. So things like that, that does happen over and over, and and people have to start with concern with technology. So as a researcher, we think that one way to address those society concerns is really trying to promote a direction of biometric research. We call it the trustworthy biometrics. Now, according to the English words, trustworthy means that you are able to be relied on as honest as well as truthful. So if we apply this kind of definition into biometrics, what do we really want, right? We want to have a secure biometric systems, such as we have a truthful inputs, right? We would like to detect any spoof or forgery kind of biometric samples to make sure that the input data to a system is truthful. Secondly, we also want to have a robust, biometric systems, which means that we also have a truthful input by detecting any adversary samples, within the input, right? Input should be original sample without any modifications. And the biometric system also has to be fair regarding its output, right? We want to have an unbiased or fair output across different demographic groups. And the biometric system also need to be interpretable, means that we want to enhance the trust between the people and between the user as well as the systems by having interpretable output. We want to tell people what's the reason where the biometric system is making such decisions, right? Why we accept a match or we reject the match. Finally, you can also have a privacy systems, right? We want to protect the privacy. We want to have a privacy preserving biometric systems. So these are the few characteristics, as we define the trustworthy biometrics. Now, for today's talk, because of interest of time, I like to focus on the first two areas and maybe briefly touch about the fairness as well as interpretabilities. So let's start with the first part on the security. So as we said, this will be trying to having a truthful input by detecting any spoof as well as forgery biometric samples. So to start with, let's look at how in general a face recognition flow kind of works, right? So you have input data, you input subject, you capture by a face recognition systems, by cameras, you send into a systems, then eventually you might have a match with particular gallery, right? So the output of the match decision can be used for cell phone unlocking, maybe financial account setup, gate access, and so on and so forth. However, with this kind of systems, it's possible that an attacker can start with a presentation attack, right? Instead of having a people show up in front of the camera, it can have a cell phone, showing someone's picture and put that into a systems. So whenever that happens, right, you might have insecure systems if the face recognition is not detecting the spoof sample properly. So what we really want to have is trying to have a anti-spoofing systems, we call it FAS, right? That can be, set up in front of a face recognition systems that trying to serve as a filter that can detect any spoof attacks or presentation attacks, right? If it is detected as spoof, then you can say this is not a person, so I should not be sending this sample into the face recognition systems. In the end, the sort of downstream application can be protected. So that is a basic idea. So with this kind of FAS objective, there has been a stream of research, working on this FAS, how we detect the spoof. One of the first approach is called, direct FAS. That is, I have a very simple CNN, which is trying to do a binary classification, right? Because this is how the problem is being defined. So giving a set of live samples, I call this a 0, and give a set of spoof samples, I call this as 1, right? So eventually it's a binary decision to generate the estimation of 0 and 1. This is also how you supervise the sort of training process. However, the problem with this kind of simple direct FAS is that it tends to be overfitting, right? The reason is that, yes, you provide binary supervision to the data, but within the data, there could be other reasons we call the non-spoofing cues that contribute to the classification, such as, male or female. If your data do have a bias regarding male-female distribution, it could be wearing glasses, not wearing glasses. It could be skin tone, right? It could be the head pose. So any one of those could potentially contribute to the spoofing-based kind of decisions. So whenever you have non-spoof cue contribute to the process, then eventually, the system you trained is not going to generate well from training to testing data. So how do we address this drawback? Well, there has been a number of ways, people have been working on. One of the first ways is trying to do patch-based CNN, which means that the CNN is trying to do a binary classification instead of entire face. We will be doing for every single face patch. Now, the benefit for this, of course, is that you have more local information to rely on, right? Because in the end, whether spoof or not spoof, every local patch should be able to make a saying, make a decisions. So this can allow you to have, number one, more data. Number two, it also tend to be generalized well because you are not relying on the entire global face information. You are more relying on the local information to make the decisions. And second approach is trying to say that general binary decision has very few supervision signals. Why don't we have more supervision signals? Why don't we ask the network to do a few side tasks we call auxiliary FAS, right? So this kind of side task can make sure that eventually the binary decision was mostly based upon spoof signals, not based upon those other signals such as skin tone, glasses, and so on and so forth. So regarding the side task, there has been a few of them. For example, some work using depth information, right? Estimate the pseudo depth, relative depth information. Some work estimate RPPG signals. There also has been other work, for example, estimating the materials, and so a number of approach has been kind of working in this general direction. Now, in the end of the day, what we are most interested for FAS is probably its generalization abilities, right? So how well you can generalize from training to testing. Now, between the training to testing, there could be many differences regarding the data distribution. But one of the key differences actually coming from the fact that in this context of FAS will be the unknown attack detections. That is, on training data, you have certain attack types such as print attack, replay, and so on and so forth. But in testing time, you have a new unseen attack types. So this kind of unknown attack is really hard to detect. And we also call this kind of problem as a zero-shot learning problem for FAS. So previous approach tend to either train a one-class SVM, or you have a Gaussian mixture model to model distribution of the training GMs, spoofs. So we had one work which trying to specially design for this kind of zero-shot anti-spoofing problems. We call it the deep tree learning. The idea is very simple. That is, even though the testing spoof type may not be seen during the training, but you can potentially try to classify or separate your training spoof types into different category. We call it the tree leaves, right? Within each leaf, we kind of putting more similar spoof types into one leaf node, with the hope that even the testing one is not seen, but it might be similar to one of the training clusters or one of the training leaf nodes, so that leaf node may have the best hope to do classification for this unseen spoof types. So that's the basic idea. So when we do this, we design this deep tree network, which have this conditional residue unit and the tree routing unit. Eventually in the leaf node here, I show you the 8 leaf nodes. We does the supervised binary learning for real versus spoof. So the basic idea is that, giving a set of data, we recursively, put the data into left branch or right branch by using TRU, okay, this tree routing unit. And eventually all the data will be, separate into 8 different branch. Now, what this TRU does is trying to essentially look at the distribution of the data, try to find out one axis which have allowed the data have the maximum span. Okay, and within that direction, because the data have maximum span, then you can try to put them into left class and right class. Now, the way to learn this maximum span is by using principal component analysis. So quite simple, because PCA can allow data to have the maximum span, right, to find a one dimension. Of course, the feature to learn the PCA is driven by the binary classification in the leaf node. In other words, I'm using, spoof relevant feature to essentially learn this binary classification so that I can separate data in an unsupervised way into left branch and right branch. And this will be done recursively until the leaf nodes. Okay. Okay. So more recently, another line of research, when my group as well as other group has been working on is called generative FAS, which means that the CNN again is trying to do binary classification, but also generate some type of image to represent as a spoof queue. Okay, we call it the trace. Okay. So why this kind of trace is important model the trace. So let me show you one example. So here we have 4 cases, right? 4 different examples. In each example, we have 3 images. The left image is the input spoof data. The middle image is our generate kind of synthetic live sample from that spoof. And the third picture is basically the difference of the two. Okay, or the spoof trace we're estimating. So as you can see, for different spoof type, for left-hand side is top left-hand side corner is a replay attack. We have very clear Moral patterns. Top right-hand side is called funny eye glasses or paper glasses. So you can extract the spoof trace of this glass. Bottom left, I think is a makeup. So the person have very strong makeup. So we can estimate this layer, spoof trace representing this makeups. The last one is transparent mask. Okay. So why do we want to do this? Well, first of all, estimated trace allow you to be able to explain why we consider this image is a spoof, right? Because clearly by looking at the trace, you can understand that what are the difference among the different spoof types. And we can also use this for especially helping, long tail spoof data, because some of the spoof type we may not have enough training samples. So using this, we can help to synthesize data for those kind of spoof types. I'll show you more example later. So how we model this? So we have the physicist-based modeling scheme. In other words, we model the spoof generation process as two types. One is called additive process, such as the trace in the model pattern. Simply if you have TA plus I live, you will get I spoof, right? Another one is impending process. Impending process is not you are taking the live add up to spoof. Instead, the TP is trying to replace the pixel in the iLab, because this could be considered as impending process. Okay, so therefore we have a joint modeling of these two processes, as you can see in the bottom. Every spoof sample is basically coming from either the source live phase, add to this additive trace, right? Or you can having a impending region, indicator P to tell me that some local region can come from the impending trace. Okay. So with this kind of modeling, our job is that giving the input data of I spoof, we like to estimate everything on the right-hand side of this equation, which including P, I live, TP, and TA. Okay, so all four parameters need to be estimated given the I spoof. So we formulate a learning problem basically, with this modeling. Now, what's the benefit? One benefit of this process is that you can do very, sophisticated spoof synthesize process. Suppose you have a set of target alive, you also have a bunch of spoof source. You can actually synthesize a lot of data by using the combination of the target live as well as the spoof source. You can see that every row is corresponding to the subject to the left, right? But every column, they have exactly the same spoof type or spoof trace. We're basically taking the spoof trace from the top and add on top of every target live images. So with this kind of synthesize, you can see that we can use this image into the training, to supplement the training data. And in our paper, we did show that this does improve the phase center spoofing performance. Okay, so not only we have face spoof attack, but we're in the real life, we also have other attacks such as digital manipulation, such as digital adversary attacks. So let me switch the gear a little bit to talk about how do we defend the digital manipulation attacks. Okay. So as we know that face digital attack manipulation has been quite popular, and not only for entertainment purpose, but also it does raise society concerns, because deepfake kind of videos or images could be generated by using this kind of face manipulation. So there has been quite some research working on this topic. So one of the work we did about a year or two ago was trying to say that can we formulate this problem as a joint detection problem as well as localization problems. Okay, that is giving an input data. We not only try to do binary decision to say it's real versus fake, but we're also trying to estimate the so-called attention map, basically trying to indicate which pixel has been modified compared to its original spoof data, original kind of real images. So not only we do this for one kind of manipulation type, we also did it for multiple manipulation type, including expression swap, identity swap, and attribute manipulation, as well as interface synthesis. You can see that for the interface synthesis, the ideal kind of target map should be everything being kind of manipulated pixels, right? But for any three types, you can see that only local pixel is indicated they are being modified, but some pixel will be still considered as real pixels. Okay, so that's kind of the objective. Now, how do we do this? We formulate a process that we think can leverage a different amount of supervision, because sometimes you do have supervised kind of the mask to tell you which pixel has been modified. In this case, we're using the supervised learning, but sometimes you have to use the weakly supervised learning. For example, a few pictures they have been they have ground truth mask, but for the most of data you don't, right? And in extreme case, you might have totally unsupervised learning process. You don't have any supervision to tell you which pixel has been modified. So how do we handle each one of these cases? So that's the purpose of this sort of network design. So with this, we show you some of the results. Here you can see that the top row is the original live images. They are real images. The second one is manipulated faces. Okay. So you can see that the second set of columns are basically entire synthesis, and we have attribute manipulation, expression swap, and identity swap. Now, row number 3 is our estimated manipulation mask. You can see that, row number 3 is actually the ground truth one. So you can see that they are pretty high quality, ground truth. But the last one is the estimated one. You can see that estimated one more or less covers the similar regions in terms of modified area, but the detail, the pixel at pixel level is far from accurate. Okay, still very, very hard problems. And so we think this is still a good problem, sort of unsolved problem, and there will be quite some research necessary to correctly estimate the manipulation areas. Okay, so one of the recent topic we are interested in this kind of digital manipulation is unknown attack detections, right? Because people typically use GAN models to generate the attacks. So between training and testing, you can have different GAN models, right? So how do we deal with this situation? So let me show you one example as a motivation. Suppose, let's say on Monday, Los Angeles time, right, receive some images or news articles, right? Similarly, on the same day, New York Times as well as the Washington Post, maybe also receiving news articles. And so one thing typically we need to do is trying to do anti-deepfake algorithms, running algorithms on the images, right? Make sure they are real images. And with the running, maybe we figure out that, sorry, this seems to be considered as fake. So if it's fake, one thing we like to do is trying to do model attribution. That is, it is trained from n sort of non-generated models such as star GAN, BN GAN, and big GAN, and so on and so forth, right? So we like to say that for each one of the fake data, which one of the GAN may be used to generate the fake images, okay? And unfortunately, in the running, maybe figure out that, sorry, I cannot really identify. They are basically unknown. So in that case, the question we like to ask is that, is this a coordinated misinformation attack, right? In other words, are all the fake images coming from the same attackers or same models? So this is what we want to answer the question. But right now, I think that most of the current work is not able to answer a question like this. So we think the main reason is that, most of the model attribution work are trying to treat every single GAN model as a separate or isolated classes, right? Let's say I have 10 different classes of models, star GAN, B GAN, and so on and so forth. I call them as model 1 and new model 10. So they're all separate, right? But ideally, what we really should be doing is trying to learning a continuous embedding for those GAN models so that I can map those GAN models into the embedding space. Now, the benefit of this embedding space is that now in the embedding space, you have a concept of distance of similarities, right? Some GAN, because their architecture design, because they are loss functions, they may intrinsically more similar compared to others, right? Some are less similar compared to others. So if you can do that, then when you have these three different unseen or unknown generating models from the previous slide, now you can map them into this embedding space. If in the embedding space, they are actually very similar to each other, that means that it's likely this will be a coordinated attack. So that is a basic motivation for this work. So we call this problem as model parsing. The basic idea is that different generated model, they are being different because people use different network architecture as well as a loss function, right, to design the generated models. So with those, we have the generated models, and with generated model, we can generate images, fake images. And we have a fingerprint estimation network to estimate the fingerprints for both real as well as fake. And then for the fingerprint of the fake image, we send into the model parsing network, which reverse engineer the process and try to estimate the network architectures that were used to generate these generated models. So that is the basic idea we call the model parsing, basically estimate the network architectures, parameter, as well as the loss functions. Okay, so without going to how we did it, so these are some of the examples that, for example, we designed a approach to basically do reverse engineering to estimate the network architecture. So here you can see that we estimate, whether we have nonlinear how many nonlinearity in the block, right? Whether we have upsampling layer, whether we have downsampling layer, whether we have skip connections. So these are the discrete parameter estimation on the left-hand side. We show you the F1 score. So the higher, the better. On the right-hand side, we show you L1 arrow for the continuous parameter estimation. For example, how many fully connected layer, how many pooling layer, the total number of parameters, so for how many convolution layers. So each one of the parameter is being estimated by our systems. You can see that this clearly is a fairly ill-posed problem. It's hard to estimate. Certain parameter is relatively easy to be estimated. For example, whether we have downsampling, whether we have skip connections. So that kind of information in the architecture actually could be estimated by looking at the GAN generated data. So again, this is the reverse engineering. You start with the GAN generated image, you ask what kind of model, what kind of architecture was used to produce these images. Okay. So we collected more than actually 100 GM models, generated models, and these are for each one of them, we estimate the fingerprint, then we compute the confusion matrix among the fingerprint of different GMs. So by looking at this, you can see that each one of them seems to have a unique fingerprint. And there's a group of, a cluster of GMs. They are actually quite similar to each other by looking at the fingerprint. This is understandable because you can see that by looking at the name, you can understand that they are mostly kind of families or siblings of GMs, right? They only have small modification of each other. That's why their corresponding fingerprint are relatively similar to each other. And that's why you can see this kind of the block matrices in the middle indicate their similarities. And the fingerprint concept is not new for general images, for real images. For example, this is the kind of one of the previous work. We take the live images or genuine images, and that's the first row, trying to estimate its noise patterns, and then we convert the noise into the FFT domain, a frequency domain. And so you can see that the third row is especially interesting. So these are the FFT of the noise of different live images that's generated by different cell phones. For example, iPhone 4S and iPhone 5C and the Xiaomi and SM. Different cell phone captured data. They actually have very distinct fingerprint. So this kind of concept has been essentially leveraged into the GAN image modeling. We think, GAN image will have different fingerprint as well. Okay, so this work has been widely reported to do not in different media groups and for doing the model parsing. We think this is a kind of the new problem to be studied, going forward, especially for detecting unknown attacks. Okay, so with that, let me switch to the second part. We call it robustness. Okay, so this is try to essentially detect try to make sure the input data is truthful by detecting adversary samples. So as we said, this is one of three kind of possible attacks, right, to the systems. So the general idea is that let's say you have a real probe. If you send into the adversary generation process, you may generate adversary faces, right? So the adversary faces may have a smaller, matching accuracy, matching scores compared to the Gary data. Now the original imager will have very high, matching score, 0.72. It is larger than 0.28 is a threshold. So originally it was a genuine matching, but because of adversary attack, you can make this to become a non-match basically. So we call this as obfuscation attack. So there has been different kind of defense scheme for this adversary faces, right? Number one is that you can have a pure detector, basically trying to detect adversary images, right? And just like anti-spoofing, right? If it's adversary image, you reject him. If it's live image, you send into face recognition. So it serves as a filter. The second scheme is called purification. That is, I don't care whether input images are virtual or real. I always send them through a purify, right? If it's a real image, I don't do anything for the purification, hopefully. But if it's adversary, I will make it clean and then send into automatic face recognition systems. And the last one is trying to say that why don't I train the AFS systems that is robust to adversary attacks? Okay, and you can see that each one of different idea has its own pros and cons, right? For example, for the last one, you don't have any additional models, so the inference time will be faster, but inevitably you will lose some accuracy because your face recognition system will also care about robustness, right? But for the purification, the risk is that it might do something for the real data. It cannot guarantee for the real data you don't do any processing. Okay. So what we propose is a system we call the face guard. Essentially does two things. Well, actually, three things. That is giving input data and this enroll face. If we have adversary image who have lower score, let's say 0.28 instead of the real data 0.85, I am going to do three things. Number one, I detect this is adversary attack. Number two, I localize which pixel has been sort of modified, right, spatially. And finally, the purification try to say that, can I recover the real image behind it? Can I remove the adversary perturbation noise and recover the real data? You see, if I can recover, the matching score can increase from 0.29 into 0.78. Okay, so that is the basically what we like to do, and we have a simple kind of approach to achieve that. So without going to the detail, and some of the results including that in terms of detection, the system can detect a wider range of attack types. Actually, for the 6 different attack types we show you, FGSM, PGD, and so on and so forth, each one of them is actually not in the training process. We have automatically spoofed the adversary data generation process in the training. So that's not connected to a particular kind of attack types as we seeing during the testing. So this is more like unseen kind of type detection. So in general, the performance is pretty high. In terms of purification, as you can see, right, for a system, I think we take LFW, we attack it, and if it's no defense, you can see that the adversary pair, recognition rate is very, very low. Okay, it's used to be 99, but because of attack is successful, so without any purification, your matching rate is very low. But compared to previous approach, either previous robustness approach as well as purification approach, you can see that we can increase into about 77% classification performance. So on the right hand side, you can see that the first column is a real prob. The second is adversary. You can see the score is all very low, 0.19, 0.23, and so on and so forth. Indicate the adversary attack was successful, right? The column 3 and column 4 are two different defense schemes. The column 5, the last column, is our approach. You can see that the green number indicate we are able to improve the matching score from a very low one into a high matching score so that it can be classified correctly. Okay. All right. So the last work we like to talk about for the adversary attack is called the unified detection of digital and the physical face attacks. The idea is quite simple. That is, we have more and more attack types, such as digital attack, including adversary, digital manipulation, we also have physical attacks, right? Can we unify all three? In other words, for face recognition systems, I do not know which particular attack does the data coming from, right? The data can have multiple attacks, can have either one of attacks. So I wish to have a system, a detector can detect all three kind of attacks. Okay, so this problem itself is not easy. So if we take the data from all three kind of attack types and train a single model, we call the joint CNN, you can see that the overall TDR at the 0.2%, the FDR is very, very low. It's only 53%. It's almost a sort of, flip a coin, right? At that kind of performance. So why is that? So one of the reasons is that if we do a kind of correlation coefficient analysis, so this is what the triangle shows, okay? The triangle shows that based on the latent code from each one of the spoof type, if you compute the correlation coefficient between less cosmetic versus impersonation or cosmetic versus half mask, you get corresponding correlation coefficients. You can see that among the three types, so we use color code to indicate the different spoof types. Among the three types, right, the physical spoofing is quite different compared to others because they are kind of having different colors. But for the other three different groups, you can see that these four different digital manipulation are more or less similar. The next five, which including 4 different adversary plus 1 digital manipulation, they are similar. The last 3, they're also similar. So based on this idea, we try to propose a scheme that is essentially learning different branch. We separate data into 4 different branch, and we're using different heads to perform classification for each one of the cluster. Okay. So with this, we did a pretty comprehensive experiments. You can see that we take each separate model, which is the best for adversary, best for digital manipulation, as well as spoofing. Without any sort of retraining, we test it. You can see that only the diagonal element, they are doing fairly well, right? Because they are kind of training and testing with the same type. But for the off diagonal, they're doing pretty bad, okay? Same thing in the middle, we did a retraining of the those model, but retraining with more data. You can see the performance slightly improves, but overall accuracy still is fairly low. The last one, we're basically taking 3 different models, does different fusion, including cascade, right? One after another, including mean score, median score, different score fusions. But you can see that overall performance still not very good. In general, our proposed method can do a fairly good job in all 3 types as well as overall performance. Okay. Okay, so I may have, let me try to wrap this up. So for debiasing, I don't think we have time to go through the detail. But one work we were trying to do was trying to debiasing face recognition together with demographic attribute classification, because we think demographic attribute classification is a problem associated with biasness. So we have a disentangled approach to essentially debiasing both FAR as well as attribute classification. The problem with the previous approach is that it does reduce the face ranging performance. So therefore, in more recent work, we have this group adaptive classify, which is essentially trying to change your convolution filters for different demographic groups. So this approach can ensure eventually you have both lower biasness as well overall better face ranging performance. So this is the benefit of this work. Okay, I don't think I should have time for this. Let me skip this. So in conclusion, so we think this trustworthy face recognition is an emergency direction in the communities, because of both technically it's challenging as well as societally is quite important, right? The prospect of the technology itself, will be depending on how well we can address the trustworthy issues. Yeah. And finally, we do observe there's common issues among different attack types, such as robustness to PIE, unseen attack detections, right? How do you make it generalizable? How do you make it expandable? So I think study all three or different variety of attack types allow you to look at the common characteristic among different attack types. So this I think would be something interesting for the future research. Okay. That's it. I can take any questions if there's still time.
Thanks for your wonderful talk today. Is there any online questions? And you can put the questions on the chat, or I have collected 3 questions from the WeChat actually. So
sure, go ahead.
For the first question about the applicable face recognition, what can we borrow from other community like future visualization or other approaches for explainable face recognition?
I see. Good question. So I see 2 lines of research in expandable face recognition. One line of research is trying to borrow from general object recognition. People do different kind of visualization, right? Using visualization spatially as well temporarily to understand how face recognition works. Okay, I think this line of research has the benefit of help us understand the behavior of the face recognition. The second line of research, one of example is this work that we published in ICCV 2019 was trying to directly change the face recognition loss functions with the purpose that eventually the face latent code is more expandable. Okay, because in general, face latent code is describe the entire face. It doesn't have explanation abilities, right? When you match with 2 different latent code, you cannot say much about why this is a match, why this is not a match. But this work trying to say that if I can associate different part of latent code with the different facial parts, such as eye, nose, mouth, then eventually when I match with 2 code, based on the result, I can say that this 2 face is similar in the mouth, but maybe not in the eyes, right? So that kind of explanation can be provided in terms of results. So I think this, I think both line of research is interesting, but I think for the second line, probably there's more work could be done to add in more and more interpretability into the latent code, because I think the latent code, there's still a lot of room could be played. Okay, yeah.
Okay, thanks for your answer. The second question is about face recognition with privacy. Is training with simulated face promising direction? Could it defeat real world data like Microsoft 1 million?
Yeah, very good question. I think this is a question that we are interested as well. Actually, Dr. Jian was telling me that he and his students was working on, doing fingerprint image synthesize and then compare the classified trend on completely synthetic fingerprint image versus the real kind of fingerprint image to see what's the performance. I think we got to do the same thing for faces as well. I believe this year in ICCV, we had a recent paper from Tencent, right? If I remember right. And that was about training face recognition system on the synthetic data. I think definitely going forward, it's become more and more possible to do that. But I think the real most important experiment is probably to say that, let's say you have a real face database. You can train face recognition system on that database, but you can also use the same real face database to synthesize millions subject. And then you train face recognition system on that millions of synthetic data to see what is performance. So the real question is that, does the face synthesize process producing more identity information? If it does produce more identity information, then I think the face recognition system can benefit from it if your face recognition is trained on those synthetic data. But if the face synthesize process is not generating new distribution, right, in terms of face identities, then I would say that the face recognition system trained on synthetic data will not pass the performance of the training compared to training on the real data. So I think the tricky is mostly on the synthesize process. We have to understand whether the synthesize process actually generates new identity distributions. Yeah, so that's my take on this.
Okay.
Yeah.
Okay, thanks for your answer for this question. And there are last question on, it seems that there are some difference between face generation and natural object generation. Is face generation more difficult than natural object, and why? So yeah.
I think I think they are probably I would say face generation to me is on the generation side that might be simpler compared to other objects such as chairs, because you have much more self-occlusions for image generation, right? The transparent object is also harder to generate. But face generation has its own challenge, mostly because we see lots of faces. We are much more sensitive on the quality of synthesized faces. So in other words, the bar is much higher, right, for face generation. So because humans are so sensitive, humans are very good to pick up any mistakes, any noise in the generated faces. I think that part make the face generation to be hard. Okay, but in terms of generation technology itself, face not necessarily the hardest one. Yeah, that would be my take.
Okay. Is there any other questions? Is there any other online questions here in the Zoom chat? I haven't seen any. Okay. Thanks for your brilliant talk today. Thanks again for Professor Xiaoming. Okay,
thank you, Jiankang. Yeah.
Bye.
Okay, bye. Yeah, take care. Bye.
This is the time. The third talk is from Professor Rama. The topic is fair face recognition, and Professor Rama is a Thornburg Distinguished Professor with Department of Electronic and Computer Engineer and Biomedical Engineering with a secondary appointment in the Department of Computer Science, Johns Hopkins University. Before joining JHU, he was a distinguished university professor in University of Maryland. And Professor Rama received the King's Prize from the International Association of Pattern Recognition. And he also received a lot of other awards from the community. Professor Rama served as the editor-in-chief of ICCV T-Parmy. He is a Golden Core member of the ICCV Computer Society, served as a distinguished lecturer of the IEEE Signal Processing Society, and as the president of the IEEE Biometric Council. He is a fellow of IRPR, OSA, ASM, AI, and NAI. Welcome to Professor Rama's talk today. So,
all right, can I share my slides?
yes. Let me stop my sharing.
Okay. All right. Can you see my slides?
Yes, I can see your slide.
All right. Thank you for inviting me to give this talk. So I'm going to briefly discuss our work on face recognition and then discuss the issues that have come up maybe over the last few years, in particular bias. Bias is not peculiar to face recognition. We also see that in other problems such as vehicle re-identification and so on. I guess anytime you use data and data only, if the data is not properly collected, one can expect to see some issues. And statistics literature has a lot of work on handling bias. You know, anytime we do an estimate, we usually try to estimate, also come up with an estimate of bias and variance. This is true for parameter estimation. This is true for decision rules and so on. But the problem here is we are dealing with a very highly nonlinear and hierarchical regression machine, the so-called deep learning. I like to call it deep fitting. I think the learning is more sophisticated than fitting. So it's basically we are fitting, nonlinear regression models to data. So, but we're not able to analyze the bias in a theoretical way. Okay, so, but this is important. What we are seeing is that bias in face recognition has now morphed into bias in AI, the larger AI, the general AI. Unless we really take care of this issue, we will continuously face some opposition to this technology. Okay, so this is an old story, but I like to point out sometimes we realize issues with our approach only when we do at-scale problems. Of course, I should be very careful about working in at-scale problems when Mr. Patrick Rother is in the audience. He is the one who is really doing at-scale problems, evaluating them for face recognition. But I think Janus, I thought, is one of the first programs where we had impressive amounts of data to try out some new approaches using deep learning. So here we have a brief list of things we did for Janus, which just ended last year, I think. Yeah, July 31st, 2020. So we have a generic setup, and you can do a multitask approach for detection, landmark points, visibility estimation, pose, gender, etc. Once you have this bounding box, and we train two separate networks, one based on ResNet, one based on Inception, and then we fuse them and etc. Okay, there we have a lot of papers on this. As you can see, if you are in our gallery, we'll be able to tell you who you are, and gender, and your pose and things like that. Of course, Janus really extended the operating conditions by looking at what is known as IJBS. CS6 is what was made available to the program participants, and there is an IJBS, but I don't think IJBS got distributed widely. I only see a very few papers that report results on that, ours included. And of course, the other one, IJBB, is part of IJBC. And these are both very challenging data sets, not in terms of the number of subjects, but in terms of the acquisition conditions. As you can see, CS6 is the version of IJBS is the publicly releasable version. It was not done, but CS6 is what we work with. So you can see, enrollment is in school. And then you have various places where the faces have been acquired. And we have worked with that. And of course, we have also worked with a very large gallery face data set, 14 million images. For academic standards, this can be called an at-scale problem. 4 million distinct individuals. They're not US citizens, and a very particular demography. So we learned a lot of things by doing that. We can't publish any results on that. We can't even tell you anything about this data set, but working on this large number of identities showed us some interesting behaviors of deep learning networks that are trained on such large data sets. And we also worked, and we have already published face recognition at distance, 300 meters, 650 meters, 1,000 meters. There's a paper in T-Biome last year, I think, or maybe this year. There's another paper in Journal of Special Topics and Signal Processing. And we did another amount of work, a lot of work on something called IJB-MDF dataset. We have not published it yet. We are still working. The gallery is visible, and the probes are all sphere data at various wavelengths. So, face recognition, we were all quite happy. We're doing it. Things seem to be working. And as you know, before 2012, computer vision and working were not in the same sentence. Since 2012, we seem to see that more often, which is good. But then we came across this, work, gender faces that most of you may be aware of. Some commercial software systems were tried for gender recognition with two different kinds of data sets, and suddenly, it was found that it has bias. I think Patrick has also done a big report on this. Anyway, of course, Amazon was somewhat put on spot, I guess, so they had to come and quickly, fix it. I don't keep track of everything that happens because things are just moving too fast. Maybe this slide is outdated. Maybe Amazon is even doing better than what's portrayed here. So when we saw this, we said, okay, we are also building face networks. My good friend, Professor Stefano Ciffrilio at Imperial College has also built ArcFace. ArcFace does have better performance than what we did for IJBC, but ArcFace has not been evaluated on other data sets such as IJBS and so on. So with these deep learning methods, if you have to do well on one data set, it's good. But if you have to do well on a whole bunch of data sets, it's slightly a different problem. So we wanted to understand what the issues are here. First question we wanted to ask is the deep features that we extract using our approach, do they also code other information? Does it represent gender strongly? Does it represent age and things like that? Okay, so when you look at a particular problem, it's sometimes easy to figure out the things that can make the problem solution is dependent on, right? Pose an object recognition problem, pose is a very natural thing. And in the case of face, age is also a natural thing. Of course, gender is a natural thing. And skin tone is a natural thing. So we wanted to find out how much of these things are represented in our features. So, my student went and looked at a way to compute mutual information between features and attributes. In the case of vehicle re-identification problem, we see camera bias. You have multiple cameras, city scale, actually countrywide, right? There are thousands of traffic cameras we have. Every camera introduces some kind of a domain shift, okay? So if you develop your algorithm using one particular camera, the camera bias seeps into it. This is true with pathology. In digital pathology, people collect specimens in various labs, and they use different staining processes, and they introduce certain kinds of biases. So this is a problem we have to address everywhere, right? So the case of face, we thought we will do this, and so my student went and this is a needed view graph for some equations. I won't belabor you much on the details of this. This is published work and we have used it. And there is a FG 2020 paper where we discuss how we calculate these things. So we find age, gender, and so on. We took two networks. Hello? I'm hearing some cross. Okay, thank you. Okay. Can you hear me well?
Yes, I can hear you. Sorry for the interrupt.
Yeah, that's all right. Thank you.
Muted.
Thank you. So crystal phase is our network, and and then we have arc phase. Okay, so we did the following thing. We monitor how these the attributes, the pose, and gender are reflected in at various layers, and how they change as we do the learning process. So we do, we can see in the earlier, this is not surprising, right? Because as you know, back propagation works from top to bottom. So ID is the thing we give, but I think one of the reasons why we have the gender creep, as I like to call in our features, is we use a multitask approach that I just mentioned before. And so our bounding box, detection process is done simultaneously with gender, with pose, and whether you're smiling or not, and things like that. So because we thought doing multitask would help some tasks for which you don't have a lot of data, for example, pose estimation or fiducial landmark estimation. Usually the size of annotated data for these tasks is less. But in the case of detection, putting bounding box, it's pretty good, right? You have a lot of data like that. So we do this, and as you can see, first pose, and gender are strongly expressed, and then finally identity takes over. Is somewhat unlearned, but the other things are still dominant, gender and so forth. So this is, during training, what happens, right? Again, you see a similar trend. There is some kind of an explanation one can give from the so-called information bottleneck theory, the two distinct phases, a fitting phase and a compression phase. A fitting phase, task relevant and irrelevant information is learned. In the compression phase, the irrelevant information is unlearned. So in the case of face recognition networks, at least the one we have worked with, it looks like only is unlearned. So the key takeaways are, at least our network seem to encode age, and gender. And so we have to kind of do a process of suppressing what is being expressed. We only worry about ID. We don't want to worry about anything else, right? So we did the this work. This will be presented at ICCV 2021 sometime in the coming days. We call it protected attribute suppression system. So here, there's one way to do this is to do an end-to-end thing, right? Make sure you collect the proper data set and things like that. And that takes a lot of time. And also, we still don't have an understanding about what is the proper balance in the data set. People first thought if you do proper balancing, the bias may decrease. It's not quite true. We found that as we decrease we have to decrease the number of males in the data set, so much so that the overall performance goes down. So there is this bias performance trade-off, right? So we are not opting for end-to-end approach. We are opting for the fact that there are networks that are already available. Unfortunately, they are biased. Can we go and kind of take care of the bias issue? So what we do, we start with the pre-trained network, freeze the network, take the features, and then train another model, M, and then we classify using this features that go into the this network, and then we have a classifier, and then we have an ensemble classifier. This is E1 could be age, E2 could be pose, E3, EK can be gender, and so on. And so we have another loss function. We call it the debiasing loss function. And so we go through the whole process together. So this is like taking the existing features, and if the features show some strong expression of gender or a skin tone, sometimes they do both, sometimes one is better. For example, in ArcFace, we found it doesn't show a lot of gender expression, but it does show skin tone expression and things like that. And so we, combine this process of suppressing the expressed attributes, and you can do it sequentially with the details are in the ICCV paper, and I won't take the thunder off my students' poster. So please look at that poster. Prithvi there, and a few other students, and so on. You could also do sequentially, but there's no guarantee. If you make your thing unbiased to one attribute, that will not affect the other. So you can try to do them simultaneously, and that's what we call as multi-pass. And so how does this work? Well, you can see the diagram. Without doing these things, we have, we show the ArcFace situation and pass, and then multi-pass and so on. As you can see, the maroon color bias, gender bias is lowered. We took ArcFace, and we can do this and lower the bias in ArcFace. We can do the same thing for a skin tone, but it is still at at that level 0.06. Multipass didn't do much improvement corresponding to mitigation to bias towards skin tone. And then we did the same thing for our network, which we call crystal phase. And the pass seem to do better than multi-pass. Sometimes these things are hard to predict. And you could see the skin tone bias also is reduced, right? So this is now doable. We have done similar things for the vehicle re-ID problem also. So you could figure out what attributes your system is not happy about, and then try to suppress them. But the thing is, you have to do that with keeping performance in mind, right? You have to have the oftentimes when you reduce bias, you may reduce performance. So my student, Mr. Prithvi, there came with this bias performance coefficient, he calls it, a drop in bias and a drop in TPR, right? So you can now look at various possibilities and see where the range of BPC will be. The higher it is, better. Of course, there may be some anomalous situations where, in terms of bias TPR, which usually we don't see. So this is a reasonable metric, and one can relate this to one of the existing fairness metric. That's another issue, right? If you see a recent survey article, there are about 23 ways bias can be introduced, and about 12 or 13 different metrics. So this thing is still not clear. First of all, it is task dependent, right? What bias is task dependent. So this is going to evolve. But the thing is, a bias in face recognition, as I said before, has morphed into a bias in general AI, and that is creating all kinds of issues. There are groups looking at whether regulations should be introduced and so on because of the perceived bias. This becomes even more serious in medicine. So we do the multi-pass system for ArcFace, skin tone bias, and you can see what the performance of the BPC is. That is 0.805 with ArcFace features when it comes to gender, and when it comes to skin tone, it's 0.519. And of course, we have to look at low. One of the things Janus did is that it took us to the so-called dark regions, 10 power minus 6, 10 power minus 7, etc. Right? In the early days, we couldn't do that. So this is our thing, and you can see 0.833 multipass, pass is 0.847, and so on. So we are encouraged that this is a useful thing to try. And then we do comparisons with end-to-end systems. And you can see we require fewer parameters than end-to-end counterparts. I think if you want to do simultaneous bias issue with gender and skin tone and so on with the end-to-end, it's going to be quite challenging. Then here we have a 10 power minus 5, what the performance is and so forth, the verification performance. Anyway, so these are the numbers that we report in the ICCV paper. Of course, as you know, visualization has become an important tool, thanks to Toralba's work and then the work of Devi Parikh and Dhruv Batra, CAM, grad CAM, etc. So you can now see what exactly happens. Now, it looks like in the case of male, female, the networks seem to attend to different spatial regions. And the same is true with the dark skin tone and light skin tone. The question then is, if we massage the attention network, or one way to show that things work better is to do the before and after activation maps for these, systems I have, pass, multi-pass, and so forth, right? So then you can see whether the attention map is not too focused on something. That is the thing, right? There is a trade-off. You want to capitalize some unique features in your classification work, but if that also introduces bias, then you have to be cautious about that. So one approach to think is, can we make the attention maps to be somewhat looking similar, whether it's a male or a female, or it's a dark skin tone or light skin tone, and then see what would that happen. We are working on that as a way to reduce bias. Okay, and then after the work we did, we have we thought we would use some kind of a knowledge distillation procedure for bias reduction. This work is in collaboration with Dr. Jonathan Phillips. Here we have, student teacher configuration. The teacher, let's take the gender. The teacher will, just work with making it, just working on one attribute, right? The gender, just male maybe. And then the network, once it converges, that information that is passed on to the student network as an initialization. The weights are used, and this is how the knowledge is sent. And then the student will work on the other, the female, data sets and so forth, right? And then you have the distillation loss, which is kind of the cosine similarity between FS student feature and the teacher features and so on. So we found that this to be an interesting approach. The idea here is the teacher is being a very experienced person, is probably not as biased, and so that knowledge can be sent to the student. Of course, in the first version we had, the student did train on the entire data sets again. So we thought we will also let the student do this. So this is, identity classifying ability of the students. We had one more step, which is called DD++, and train a new student, MS star, and MS as the teacher network, and distills unbiasedness to MS star. Okay, so there are multiple ways to do these things. One of the things most of us now realize with deep learning is there's just an infinite number of variations you can introduce and so on, right? So this is interestingly doing well. So what happens here is, dissimilar attention regions in the original crystal phase, as you can see, for males and females. And if you look at the attention maps for D and D, this looks somewhat similar. So basically, as I said before, one can evaluate the effectiveness of your bias mitigation systems by looking at attention maps before and after. And without this bias mitigation things, you would see that the behavior or the structure of the attention maps will be different. for males and females. And as you do for D&D and D&D++, etc., it's there. But as I said, the catch is, as you do it, you got to maintain the performance. So this is one of the reasons why we are moving towards taking the existing systems that are performing very well and then try to handle the bias issue. Okay, if you do a lot of end-to-end, there's no guarantee that you will really have the high performance that the so-called bias networks have. So again, it's our approach. That's all. And this is the same thing with crystal phase. As you can see with the DND and DND plus, you have a better, more even activation map. Right now, we can ask the question whether this is good or bad. Well, if the activation maps are not too perturbed by the gender or the skin tone, then I think it may be a good thing to do. Okay, so this is an ongoing work, and so we have not published it yet. Okay, so this is the baseline we have compared with various available method at 10 power 4, 10 power minus 5, etc., gender bias and skin tone bias. So you can see DND plus plus, DND is ours, and DND plus plus for gender, so forth. So one of the things that you do find when you work with data-driven methods is it's very hard to predict. You may have the proper rationale, but there's no guarantee that you will see it when you use data. So, we have to do some more work. As you can see here, the DND plus plus is a slightly more biased than DND in the left gender bias situation, and it's the same. It all depends on at which 10 power minus 3, 10 power minus 4 you are looking at, right? So if you see here for DND plus plus, it's the lowest, right? So another way to visualize these things is the plot, a kind of a 2D plot in terms of where the various systems are with respect to performance and bias, right? That's what's important. Nobody likes being biased. So you would like to be in the left upper corner, right? High performance and low bias, both gender. This is the left figure. That is the right figure. As you can see, DND plus is to the left of everybody and to the top, and so on. So you can put various algorithms in this plot to see where various systems. So bias is not peculiar to face recognition. We work on vehicle re-ID. It's a really at scale problem. We have access to thousands of traffic cameras, and at city scale and countrywide. And so we want to find out if a car seen in one view is the same when it is seen in the other view. So we built a system. This has been reported in ICCV 2019 and ECCV 2020. And then we also participate in the AI City challenge that has been going on with the CVPR since 2019. I want you to focus on three things. The left pre-processing block has two boxes called domain adaptation, because the way you train these algorithms is you have to use the existing curated data sets, UAD track and a few other city view and so on. The operational systems or the traffic cameras that you see, they generate all kinds of video data, and you really can't annotate them, right? It takes forever to annotate these data. It's just like, it's just working, 24/7, right? So we actually annotated 34 hours of that video. And what we do here is we take the good data for which annotations are available. We will reduce the quality of the data to match that of the traffic camera data. And so we carry the annotations and we train using that. This is the domain adaptation thing, because there's not a lot of annotations available for these kinds of traffic cameras. On the rightmost, and of course in the middle box, you see some things. We have some attention mechanisms and so on, some self-supervision and things like that. These are discussed in the paper. In the right box, you will see, same camera bias removal. That's the thing. So we found that there is bias here to cameras, which are dominantly used for training. So you have to kind of collect data from different cameras, and it's like taking female faces from different countries and creating one data set for females all over the world. That introduces an issue. While the training data set is somewhat diverse, whether the network can really learn the concept of females if you give such a varying source data set, right? So again, in the case of vehicle re-ID, in the face, at least you can put some restrictions as to how the faces should be collected. In the case of vehicle re-ID, the cameras are cameras. They're going to collect, the vehicles will be in different poses and so forth. So it's generating a proper curated data set is a harder problem. So there is this way we can do the orientation bias removal, camera removal, and so on. So basically the point I want to make is, while we are all consumed or we are all paying attention to bias in face recognition, there is bias potentially in every data-driven system built using deep learning. If we are not hearing about it, it simply means we have not looked at it. So I assume we would see that in digital pathology. We are seeing it here in vehicle re-ID and any other decision that is made using data, because the data balancing is not the solution to it. It's not clear. First of all, in some problems, we may not even know what we are biased towards, right? In face, it's obvious: gender, skin tone, age, maybe, hair color, it's a hair, whether the hair is there or not. A couple of years ago, we published a paper in T/M looking at 7 attributes and how the performance changes. These are called covariates, whether the face was collected indoors or outdoors, whether somebody was wearing glasses or not, whether hair is visible or not, etc. Recently, I came across a paper, thanks to Dr. Jonathan Phillips. It talks about 47 such attributes that they have looked at and to measure how the performance can change. So one could conceivably have to design a system that addresses some of these attributes to which the performance change is observed. Okay, so I'm going to kind of end on a note where I say at scale problems will reveal the what's in face recognition. This is true in machine learning, and NIST work is a great example of that. And the designers should consider bias or perceived lack of fairness. As you know, AI is come back, but what AI means now is very different from what AI meant in the 70s and 80s. In those days, I took my first course in AI in spring 1978. So we were focused those days on search, which is still being studied, and logic, first order logic and calculus using logic and how to do logic-based systems and so forth. The mid-80s, Bayes networks came and so on. But now everything is AI, right? If you ask anybody whether you're working in AI, they said, yep, absolutely. So it looks to me that other than taking matrix inversion, SVD, or fast Fourier transform, everything else is AI these days. So, but AI has become data-driven, too much so, and then you have issues. So we have to look at every deep learning network that we build. We have to be able to measure what it is biased towards, against, for, and how much is it. There has to be some kind of a metric. I'm sure the smart folks at NIST would figure all of this out. And I'm going to stop here. I think might have just probably taken 35 minutes or so, which is fine. If there are any questions, I'm happy to answer them. Thank you very much.
Okay, thanks for Professor Rama. Thanks for your wonderful talk. There are several questions in the Zoom chat. Let me read it to you. And the first one is it possible to maintain the ID information while changing his or her race, even gender? Is this pipeline helpful to reduce bias in face recognition?
Can you repeat that again? I didn't get the question.
Okay, sorry.
Is it there in the chat?
Yes, yes, in the chat.
Okay.
In the chat.
Okay, let me stop sharing and then I can look at it in. Okay, all right. There, I see that. Let me just go ahead and see. Okay, the first question is this. Hello, sir. I've been working on. That's the first question. Any pre-trained face again for? Okay. Right. In fact, what I'm saying is that I prefer, starting with the pre-trained models because there are lots of them. End-to-end training, I don't know, at some point, Patrick will answer this question. I'm going to put all of these on Patrick, whether end-to-end training is systems are better or whether taking existing systems and doing bias mitigation. We don't know that. With deep learning, there is no theory, unfortunately, right? It's so empirical. Unless you try it out on a reasonably large scale problem, we don't know what's going to happen. But we chose the approach of taking existing because I wanted to compare with ArcFace. I wanted to compare with our network or any other network. So we thought we will give a procedure for reducing bias with existing pre-trained network. So our pass is just that. Okay. But I think eventually there would be systems that would be submitted to NIST, with end-to-end things and the kind of things we do, and maybe there will be other options, and they have to go through evaluations, and then we'll find out, which is the better approach. I do believe, given the absence of theory, we have to rely on large-scale evaluations done at NIST as a way to guide us. There's just no other way. If I had a theory, then I would tell you, if you do this, you have to expect this much of reduction. But these are nonlinear hierarchical regression machines. We have absolutely no theory. Anybody has theory, they have it for 2 or 3 layers, and they don't extend to deep layers. So we are working on this. There is a part of a Muri. I'm involved with some optimization, approximation theory folks, trying to come up with mathematical models for deep learning. We're just into year 1. 4 more years, hopefully we'll figure something out. But isn't that the art thing? Before deep learning came, computer vision had a lot of good mathematics. We used to do differential geometry and stochastic inference and invariances and so on. All of this is gone now, which makes me sad sometimes, but it's okay. Now let me go to the unbiased problem from unattributed design specific class. Yeah, I think it's possible. I don't know of any specific work that has done, but yeah, definitely, it's possible. The third one is how the attention differ between RGB and thermal images. Yeah, okay. We have done that because remember the MDF data set, multi-domain data set. The video EO, visible images are the gallery, and the probes are all sphere of various types, various wavelengths. And so we went through this and we have done that. We will probably publish it sometime soon. The only problem is that nobody else other than the original data collectors, Nathan Kalka, they published some work on MDF. They compared the 2 systems from Janus. Otherwise, nobody else has published it. As you know, if you want to have a paper published in ICCV or ECCV, any of those things, you have to compare with 5 algorithms and 6 different data sets. If you are the only person who has done it, it's very hard to get things published. The reviewers say, oh, I don't know how hard this is. I have not used this data set. So it's really frustrating. Same thing we saw happen with IJBS because Michigan, I think, did some work on that, but they assumed bounding boxes were available. We actually built the entire system, and STR, a company in Boston, also did that. So we were able to publish it in a paper. But this question comes up all the time because IJBS was not released. I think, yeah, I don't think IJBS was released. I have to check with Patrick later on that. But All the other IJB series are available, but this one is not. So it's difficult to publish. In fact, that's one of the reasons why I pushed IARPA in the early days to publicly release. Because when we submitted our first paper on Janus to BMVC 2015, they rejected it, saying they don't know what CS2 is. That was the data set available from IARPA Janus program. We should have run some results on LFW, which everybody know. We said, well, this is much harder than LFW, so this should be okay. But they didn't take it. So I went to IARPA. I said, if you don't release public data sets, I'll not be able to publish, because people will say they don't know what this data says. So luckily, ArcFace got into ACT and many others with IJBA and IJBC and so on. So anyway, I think I'm rambling here. Yes, we have done the IR thermal thing. Synthetic data, you see, the thing is, Professor Vishal Patel at Hopkins is doing a lot of work on visible to thermal face recognition problem, and he uses GANs, to produce faces that look like they are in the thermal domain. And we have not done the pure synthetic data, although more and more people are looking at it. I have a new effort with Army Research Lab where we want to explore the effective use of synthetic data for deep learning. But know that we have already done that for semantic segmentation. There are papers. We have a 2018 paper. Professor Judy Hoffman at Georgia Tech has done that. Synthetic data for semantic segmentation makes a lot of sense because the gaming industry has produced such beautiful data, and they come with ground truth labels, and semantic segmentation requires annotation at every pixel, and so it really is useful to use synthetic data, and we have shown it's reasonably effective in the domain adaptation framework. But now, we have not done it for faces or objects and so on, but we will be doing that. Remember though, if you are building an operational system using complete synthetic data, then there is also a burden that why it should be trusted. As you know, we are all very impressed with the this person does not exist.com website. It produces beautiful faces. But I'll be curious to look at the Microsoft Tencent papers. I know this was coming in, right? Because it takes care of the privacy issue and things like that. We have to wait and see how well it works on the real situations and so forth. Yeah, but that's the approach people are thinking in terms of using synthetic data. But if you go to thermal domain, if you do data-driven synthesis, then the physics is lost. Those of us who have worked with infrared image, we know how complicated the physics is. You have to start with the thermodynamics. Right? And in the absence of thermodynamics, I don't know what data-based synthesis means. It may look like infrared, but it ain't infrared, right? So I think, yeah. All right, there's one question. Since scale of FER data quite small, any thoughts how to mitigate by, what is FER? Yeah, I know this is from Mr. Darshan Gera. Facial, expression recognition. Oh, yeah, sure. I see. Oh, yeah, this is a good question. We have a paper, I think in FG 2017, where we took the existing Janus setup we had, which was which was built using a large data set for the expression problem. What happened was when we fine-tuned using the small expression data set, it still behaved like identification verification network, so we couldn't completely get it out. So we had to suppress the ID. In fact, I want to go back and look at that work in the context of PASS and distill and so forth, how to suppress the ID information. And then when you use it for expression, please read our paper in FG 2017. Hui Ding is the first author, and we talk about what needs to get done to make the network forget, not totally, to some extent, ID, and then it focuses on the expression problem. Yeah, that is there. Take a look at it.
Okay. Thanks for your answer to those questions. I think you have covered all the questions here. Okay, thanks
Thank you.
for Professor Rama. Thanks for your brilliant talk today. Thank you.
Thank you.
Bye.
Have a good day, everyone.
Ah,
Bye-bye. I got to go to Hopkins now to teach, so I may get out and then join a little later. Thank you.
Okay. Thank you. Okay, let's move to the next talk from Jian Shu. His talk today is face recognition under financial scenario. Jian Shu obtained his PhD degree from School of Computing, National University of Singapore in 2019, advised by Professor Terence Sim and Professor Shui-Chen Yan. His research interest is mainly in computer vision and image understanding, particularly face and human analytics, semantic segmentation, and object detection. Jian Shu has been working as an algorithm expert in ZLZ since 2018. He mainly worked on face analysis algorithms, including face recognition, face liveness detection, face quality analysis, and face attributes recognition. Welcome to Jian Shu's talk today. Jian Shu, are you there?
Yeah, I'm here. Can you hear me?
Okay, let me stop my sharing.
Okay, so I'm going to share my own screen. Okay, can you see my screen here?
Yes. Okay.
Okay. Is everything okay here? Am I using my camera? I don't think I'm using my camera. What's the switch? Sorry, I just stopped sharing photo. I share one more time. Okay. Okay. Now you can see my screen and hear my voice, right?
Yes.
Okay, so I'd like to begin. Hello, everyone. My name is Jianshu Li from Zolos. Today, I'm going to talk about face recognition under financial scenarios. Specifically, I'm going to talk about the challenges we are facing from the perspective of industry and also our attempts. So what do I mean by financial scenarios? I'd like to give a very concrete example of a financial scenario, which is eKYC, short for electronic know your customer. Know your customer, KYC, very convenient service provided by a lot of financial institutions. Suppose you want to use the service from a bank. You have to take the ID with you and come down to a bank branch. The staff at the bank will verify you against the ID and enter your information in the system. Then you can start using the bank account. This is the traditional KYC process. And the eKYC is the whole process which is going online. So similar to the offline KYC process, this eKYC, in eKYC process, we will have a mobile application which allows you to take a picture of your own ID and also to take a picture of yourself. Those two images will go through a bunch of algorithms, and at the very end, face verification will be performed to verify that you are actually the holder of the ID card. If the verification will be successful, the whole eKYC process will be successful. Although the process looks very simple, but it indeed has great business values. Zolos has over 100 million overseas eKYC users. in over 20 business scenarios. An end user can open an account within 3 minutes, which is fully automated with 0 human interactions. Most of our business partners are local digital wallets and local banks. Here is a small story from our business partner Bcash. Under Kuwait, the Bangladesh government chose to use Bcash, which is powered by Zolo's eKYC, to remotely open bank accounts and give cash aids to affected families. Thankfully, the whole system was integrated before COVID period. Otherwise, the government would have a very hard time doing offline KYC. Doing this, because of this remote account opening using biometrics for Bcash digital wallet, Zolos is awarded the real result winners by IDC FinTech ranking this year. Okay, now let's set aside the achievements we have made and focus on the challenges we are facing and also our attempts to solve the problem. As eKYC is a whole system of face recognition, so it's not only about recognition. We do have some upstream algorithms beyond recognition, and also because it's a financial service, we have to do everything we can to make sure we are doing trustworthy face recognition. So the first topic I'm going to talk about today is face recognition. What are the challenges we are facing in face recognition, especially in eKYC scenario? Here is a very first challenge we are facing. In the eKYC scenario, for every ID, there is only 2 faces. If you have some experience with face recognizer, you will know in order to train a good face recognition algorithm, you will have to have a data set which is both wide and deep. The wide means the number of ID in the data set should be large, and deep means the number of faces for each ID should be large. For our challenge, the web face challenge, the clean version of the data set has 42 million images with 2 million ID, and averagely speaking, for each ID, there is 21 images. So indeed, this data set is a wide and a deep data set. However, for eKYC, the number of ID can be huge, but within each ID, there can only be 2 images. The first one is the face of the ID, and the second one is the face of the face in the selfie. So if the optimization is performed directly on this kind of strange data set, you will observe that the training loss is oscillating and the convergence is bad. This is because the intra-class variation for each ID is very low, and also the training and also the forgetting effect during training is very serious. How to solve this kind of problem in eKYC? We actually try out a lot of methods such as domain adaptation, such as data augmentation. Finally, we actually found this method to be quite elegant and effective. This method proposes a semi-Siamese architecture where there are 2 networks with the same architecture and almost the same parameter. The 2 networks, one is fast updating by SGD as normally used to train neural networks, but the other one is slowly updated by moving average, which is similar in the very famous self-supervised paper MOCO. As these 2 networks are updated asymmetrically, it will learn a symmetric feature for different images. We find this kind of semi-Siamese method suits very well in our eKYC scenario. We can use one branch to extract the feature of the ID and use another branch to extract the feature of the faces. And at the end of the day, the parameters of these 2 networks will converge into one. This is what the author called shallow face learning. And as eKYC has a face recognition service, the face recognition also shares the same problem as other face recognition models. A very famous problem in face recognition is to recognize similar faces. The problem here in eKYC is that similar faces will be recognized as the same person by mistake. The common cases of similar faces in our eKYC scenario will be father and son, mother and daughter, brothers and sisters, something like this. There are also strangers who look similar, but the cases is very rare. The most cases come from families and relatives. This is because if a new eKYC service is launched in a new country or new region, the people will be very curious to try out the service within their families. That's why we have a lot of similar faces here. In order to address some of the similar face issues, we actually found that the feature from age and the gender, that is the age difference and the gender difference, can actually help here. We term our method as super feature method, which is the combination of the verification feature and the age and gender feature. Here, the age and gender feature will not necessarily come from the face itself. It can also from the document, the ID. Most of the ID will have the date of birth, which we can deduct age, and also we have the gender information. Sometimes if the face recognizer is confused whether this two person is the same or not, we can rely on this age and the gender auxiliary information to do the judgment. So by this method, we can solve at least some of the similar face cases. The extreme case of similar case will be twins or even quadruplets. For this kind of similar faces, by definition, twins are the similar face which is identical from faces. So we have to rely on other features, the features other than faces, to distinguish twins, such as eye print, iris, or even the feature from ears. So it's quite a challenging problem for us just to distinguish twins from the face feature. Another very well-known problem in face recognition is recognition across races. And we know that the existing large-scale public data set are always biased to certain races. And we also actually have the similar observation from our own scenarios. Actually, we have this observation, which goes like, if we plot the normal user pass rate here against the proportion of the dark color faces, we will see actually the higher the proportion, the lower the pass rate. It means if the algorithm is unoptimized, the performance is biased to certain races. How to actually solve this problem? And we found this paper actually works quite well. This paper proposed a domain adaptation-based approach. It used the labeled source data from one race as the source domain, and also the unlabeled target data from another race as the target domain. And the feature alignment is performed by mutual information maximization. And at the end of the day, we will learn inseparable features. If the features are inseparable, it means the algorithms can perform equally well in different races. In our business scenario, we might not exactly use the different races as the source and target domain. But if we do have new scenarios and we observe some performance drop, we can use this method to catch up the performance in the target domain very quickly. It will not necessarily be a new race. It can be just totally new scenario. Once we have the method for us to adapt to new business scenarios, another problem will be occurring. That is, we might have limited or even no data in real business scenarios. We can see that from the public data set and also the faces in our eKYC scenario, there is a huge gap. Sometimes in the new scenario, we might have no data at all. If we train our model solely on this public data set, the performance will be not as good. So how to get the face of the target domain is a problem and a challenge for us. To this, we actually find that data generation is a very good solution here. I'm not sure if you have ever visited this website called thispersondoesn'texist.com. Every time you visit this website, it will demonstrate a person, a face of a person. This person doesn't correspond to any real person in the world, but it is generated by StyleGAN tool. So from the figure, we can see actually the face generated by GAN is very realistic, and we can actually do something about it. Interestingly, this paper, ThinkFace, actually proposed a method to train a face recognizer from the face generated with GAN. And from our experience, we also found the data generation very helpful. Other than generate data from GANs, we also found that data generation from a physical domain can also help. For example, if we are encountering a new business scenario and we have no data, actually from existing data, we can do some photo printing, ID making, or make some effect on the physical faces, which simulates the effect of ID face. And after that, we can use a robot arm to do the photo retaking automatically. One good thing about this physical data generation is the generated data is automatically labeled if the original data is labeled. So we found this data generation either from GAN or either from the physical domain is very, very helpful for us to train models in new scenarios. After the model is trained, how to convince the customers that actually we had a good model and we have a good performance on their scenario. This is where the public leaderboard come into place. You know, FRVT have a wide range of scenarios in their leaderboard. Even for only one-to-one verification cases, they have a wide range of scenarios. So have you ever wondered why there are so many scenarios? Because they want to make the leaderboard as comprehensive as possible. If one of the customer has a scenario which exactly match the scenario in the public leaderboard, they will happily buy in the number any company is getting in the leaderboard. And also, we are very happy to see the masked face recognition here have another leaderboard with masked face recognition and recognition for children and across different races. So even if the public leaderboard are trying to make their scenarios as comprehensive as possible, however, in the real business scenario, there will be almost some uncertainty. So if the real business scenario cannot find a scenario which is in the public leaderboard, how can we demonstrate that our method actually works very well? This is where POC and A/B testing come into place. We will actually deliver a trial version of our system and also our algorithm to the customer. The customer will do the testing on their own data. And at the end of the day, we will generate reports of the statistics they care about, such as normal user pass rate, spoof detection rate, something like this. And also another tool is A/B testing. For A/B testing, it will directly use the data online. This is really the real online data is the data in the new scenario. And with A/B testing, we will have several groups and we can divide the traffic and lead the traffic into different groups. One will be control group and the other will be the variation group where we feed our algorithm or improve our algorithm. So by this apple-to-apple comparison, we will know how effective our algorithms actually works. Okay, this is the challenges and some of the attempts we are actually having for face recognition. And for eKYC and other financial services, it's not only about recognition. We also have some algorithm beyond recognition. For example, face detection. Face detection in eKYC is actually harder than what you think. Some of the eKYC users have no idea how to take pictures of their ID because for eKYC, everybody is supposed to do it only once. So some of the inexperienced customers will take their ID in a wrong orientation or sometimes even upside down. And also, if the ID is placed in a cluttered background, sometimes there will be real person at the background. The face detector will be easily distracted by the background faces. Even within the same face, there might be multiple faces. Trust me, the current face detector is very powerful so that they can detect the ghost face or even the watermark faces. So how to select the correct face after face detection is also a problem. To address this problem, we actually have our ID alignment solution. In this ID alignment, we will use ID corner detection and also ID orientation prediction. With that, we will do ID alignment similar to face alignment to map the ID from the original image space to some canonical image space. After the IDs are in some standard space, we can actually perform much easier face detection here. And also after detection, we can do face template matching because we know the ID type, we will know from which location we should choose the face from. Another very important factor in eKYC face recognition pipeline is face quality. Although face quality is not visible to the outside, it's of equal importance in eKYC system. Because for face verification in eKYC, most of the bad cases are actually from the faces whose ID is of very bad quality. If we can actually detect the low quality images, we can let the user to retake the photo until the face quality is good. I think this is a good part of doing eKYC. We don't have to work on a fixed testing set. We can always interact with the customer and let the user to improve the image quality if needed. So the key is how to detect the quality of the images. Actually, we have several ways of detecting qualities. At the very beginning, we just use a vision-based quality detector. Here, we will manually define some low-level dimensions we care about, such as the blur of the face, the exposure of the face, and finally, we use SVM to do a summation and to give a final score. Although this method works well, but this vision-based method is generally not aligned with any downstream applications such as verification or liveness. So the second generation margin-based quality model will work closely with the verification. We will use the verification model to extract features of different faces. If the face feature is in the center of the cluster, it means that the face cannot be misrecognized. So the face is of good quality. Here. And if the face feature is far away from the cluster center, generally it means it's easily to be misrecognized to another class. So the quality of the face will be bad. After giving labels to a good and bad quality faces, we can train the network to predict the quality actually. And also in the case of eKYC, we only have two images, one ID and one selfie. Actually, we don't have the concept of cluster center anymore. In these cases, we actually design our own margin-based quality model for eKYC. Here we use the high quality selfie images, selfie faces as the reference. And with that, we find the similarity distribution of the ID face from different IDs. If the similarity is high, it means the ID quality will be high. And otherwise, the ID quality will be bad. So the similarity distribution can be mapped to a quality distribution, and then can be further mapped to either discrete or continuous quality label for us to train the network. So if we have a good quality model, we can actually increase the pass rate of the downstream liveness or verification algorithms. Finally, let's talk about face mask detection as we are doing in this challenge. In this mask, the face recognition challenge, we are trying to verify the face with mask and the face without mask. We can already see some performance drop compared to the standard face verification. How about the masked face recognition in eKYC? If the selfie face is having a mask and the ID face happen to be of low quality, the comparison here will be very terrible. But taking one step back, are masks really what eKYC wants? Suppose if you go to the bank and want to open an account, will the staff allow you to wear a mask when you are doing KYC? So for the problem of mask, the first thing for us to ask is whether mask is acceptable in the scenario. If the mask is not acceptable, the problem will become much more simpler. We can simply detect whether the face has a mask or not. If the face has a mask, we can reject the face and let the user to take another photo until the face has no mask. However, if the mask is acceptable from the scenario, it will become complicated here. First of all, should we have a mask detection algorithm to tell whether the face has a mask or not? And also because the face with mask actually have some bad effect on the downstream liveness and the verification algorithm. So shall we have separate or combined models? And also how to optimize the pass rate, especially for the normal users. So I think this is all this challenge is about. Maybe for this part, let's wait for the presentations of the top solutions. Okay, finally, our face recognition is used in a scenario which is in financial services. So we must do everything we can to make sure the face recognition is performed in a secure and trustworthy manner. Just now, Prof. Xiaoming Liu has talked about trustworthy face recognition and has a lot of coverages. And here, from our perspective, we will care more about the security of the face recognition. So for this part, the first algorithm to talk about will be for face anti-spoofing. Just now, Prof. Xiaoming Liu has talked about a lot of methods in face anti-spoofing in the academia, and we do see a lot of good methods out there. But here today in my talk, I'd like to talk about the differences between the face anti-spoofing in academia and also face anti-spoofing in industry. In academic researches, usually people are faced with a fixed testing data set or a benchmark. In the benchmark, every single sample is a static image or a single video, and the face anti-spoofing algorithm is performed on every single sample so that we can get a prediction result out of every sample. And after the whole benchmark is traversed, we can make a summarized performance such as ROC or any other thing we can have for the performance reporting. So this is the face anti-spoofing in academic research. However, for face anti-spoofing in industry, it's actually not static. It will demonstrate a feature, a dynamic feature. Suppose you are an attacker, you want to attack a new system. At the beginning, you might not know how to attack the system. You will try some simple method to attack the system, and this simple method may be caught already by the face anti-spoofing algorithm. And after you learn how to do better attacks, you will develop some advanced attacking techniques. And finally, if you are lucky, you can successfully dodge the face anti-spoofing algorithm. Once you are successful, you may want to duplicate your attacking techniques to other users or to other accounts, so that attacking in industry, the face spoofing attacks in industry will demonstrate the group property. So how to leverage these properties in industry to do face anti-spoofing is our thought, and we do have algorithms for this kind of property. Here, besides the face anti-spoofing based on single images, we also have a framework called Alpha, attack learning for face anti-spoofing. For this framework, it will have two roles. One is to search for the same person, and the other is to search for the same attack media. The search for the same person role will search the image from the historical risk data or risk feature, and look at the examples of the images which are actually linked by this linked by this same person role. We can see the same person, the person with the same ID with the same feature, with the same face recognition feature are actually linked in a same bucket. And if one of the image is marked as risky by face anti-spoofing algorithm, actually the whole bucket will be marked as risky. And if you look at the rows which is recorded by the same attack media search, you will see that this same media search actually link the attacks of the same type together. If the different tags are using the same types of face mask or same types of cell phone with similar background, actually we can put all the attacks in the same bucket. And in the same way, if one of them is marked as risky by face anti-spoofing, the whole bucket can be discovered. This is how we leverage the difference of face anti-spoofing in academic and in industry to do face anti-spoofing. As our eKYC has two input sources, one is face and the other is ID. So ID card anti-spoofing is of equal importance. Look at this image on the left-hand side. The first image is a fake Malaysia ID of Mr. B. This one, somebody do a careful PS of the photo and put it online. It looks like a real one because the PS is very detailed. And on the other hand, this photo is actually a real photo. It's one of the official Philippine photo. And on this photo, it looks like fake because it looks like somebody placed his own, her own photo on top of the original ID. But actually, the ID look like this. It's some kind of low-cost ID with only a piece of paper and some photo with plastic lamination. So how to perform ID card anti-spoofing is indeed a very challenging problem. Thankfully, for some ID, there will be security features we can use. For example, this Hong Kong ID, they do have a lot of security features. If you look at the real ID from different angles, some of the area will show different color, and some of area will show different shape. So if we try to recognize the real ID from the algorithm's perspective, there is a lot of algorithm which can be performed in order to recognize the security features automatically. Other than face image and ID image, in our business scenario in eKYC, we also have to make sure the system in which the application is running is secure. Here is where the injection attack comes into place. Here is how injection attack works. For attacker, if he might steal the image from social media, such as your Facebook, he will do some photo editing to make your photo come back to life. The photo will have the effect of eye blinking, head moving, or even mouth opening. And after this, the video can be injected to the system. By injection, one of the very common injection method is camera API hook. By changing the camera API, the application will read the data from the fake video rather than from the data from the real camera. So from the application's perspective, he thinks the person in the fake video is actually doing face scanning, but actually it's not. So system security level is also of equal importance when doing eKYC and other business and other financial services. So how to ensure the system security? Actually, in Zolos, we have the lab called FACTA Lab. This lab aims to build a world-class biometric evaluation system to enhance biometric system security. Here, the biometric security includes not only face recognition, but also fingerprint recognition and other kind of biometric modality. In order to achieve the biometric security, we actually evaluate and enhance the mobile system and hardware security. For this part, I'm not going into the details, and if you are interested, you can always contact us. Okay, here is the summary of the challenges and attempts I'm talking about here in the business scenario of eKYC. And if you have any thoughts on the challenges and any thoughts on the solutions of how to address the problems, you can always contact us. So any types of collaboration will be welcome. Thank you. That's all for today.
Okay, thanks for Jennifer's wonderful talk. Okay, let's check the questions in the Zoom chat, and we can go from the latest one and go back. So,
okay.
Yeah, the first one, could you please share more details how to search for same attack medium in ALFA, face undisposable part? How to know what the attack medium of spoofing face images?
Okay, sure. For this one, the search for same attack media works as very similar for the face search. For face search, actually you extract feature of different persons, and you can do a search from the database to search for a specific person. And for this attack media search, actually you extract feature of different attack media, such as different type of mask, different kind of cell phone, or different kind of patterns you are making on top of the lab face. So for searching this kind of media, we will have historical risk data. And for the data, we will extract features which represent the attack medias. So for every new images come in, we will also extract the feature of the attack media and search in the historical risk database.
Okay. Next one. Could you please further explain margin-based quality model for EK for face quality? What are the advantages over the other two methods?
Okay, For the margin-based quality model for EKYC, actually it is a tailor-made version of the margin-based quality model. And compared to the other models, actually the original margin-based model cannot even work in EKYC because the original margin-based model have to find the cluster center and the cluster boundaries. But for EKYC, there's only two images. You cannot find any center or a boundary. So the original margin-based quality model cannot work. The vision-based quality model will depend on some human manually designed features, which is not good as the model which is trained by neural networks. That's why they are using and designing a specific margin-based quality model for EQYC.
Okay, thanks for your answer. Another question, is there a simple way to use identity visa photos effectively in the training process? This question mentioned about training face recognition model on the identity visa photos.
Okay, so I believe this one is about the recognition of EKYC scenario where there's only two images in one ID. One is the ID or visa photo, the other is the selfie photo. So how to, is there a simple way to use the ID photo in the training process? Of course, there are some simple ways, such as you can augment the data, augment the training data, or even generate some new data to make it more than two images in one ID. However, in the Moco style training, actually the data augmentation the data augmentation was performed implicitly in the framework. So I think the method of Sami-Siamese I talked about just now is quite elegant because it embeds the data augmentation process in it very straightforward. So the simple way can use, but I do recommend the Sami-Siamese way of training.
Okay, thank you. One other question, what's the difference between the financial scenarios and the others for the same task of face recognition?
Okay, so to me, the face recognition in financial scenario and the face recognition in general scenario, they both have their own pros and cons. And first of all, the recognition in financial scenario must be very secure, because it's a serious scenario and we have to have a very strict level of face anti-spoofing and any other kind of risk we have to control. And for the face recognition in the general domain, this one is not a problem. And so this is the bad thing about face recognition in bad thing about face recognition in financial scenarios. But the recognition in financial scenarios also have its own good point. I think we can actually control the process of face recognition. We can choose which image we want use for the recognition, which image are not good. We can actually interact with the user for them to take better images. So this kind of interacting or selecting process is actually much more beneficial for the recognition network. If every image flowing to the recognition have good quality, actually the recognition can be done very easily. So I think the recognition in financial scenario and the general domain have their own pros and cons.
Okay, thank you. Last question, how to better deploy face recognition models on mobile phones? Train lightweight model or deploy or train large model, then pruning, KD or quantization. If the latter one is different from image classification or detection task. So this question is about deploy face recognition model, train lightweight model directly or pruning or compress the large models.
Okay, well, let me read through the question one more time. Okay, so this one, I believe there's a challenge of lightweight face recognition from another workshop. I think it's not this year, but previous years. I think they do have some solutions for this kind of questions. From our side, we will prefer to train it on a large model and do the pruning and model pruning and quantization. Yeah, this is the this is the case where we can use to train better models.
Okay, thank you. Thanks for your talk today, and thanks for your answer to all of those questions from our audience. Thanks again, Jianshu. Okay,
Welcome.
Bye. Let's move forward to the next step. Yes. After the keynote, and we will have the following 5 reports from the top ranked solutions in different tracks. The first one is from SenseTime, the second one is from Kako, and the third one is from Alibaba. Fourth one is from Microsoft Research Asia, and the last one is from DeepCam. So first one, SenseTime team, are you there?
Yeah, I'm here. Yeah.
Okay.
I will show in the screen. Yeah.
Okay. After each talk, anybody can ask any question to their solutions, because you know that this challenge, there are a lot of teams run a lot of experiments, and there are a lot of tricks not in papers. It is a good chance for us to ask for the details in their solutions. Yeah. Okay. Could you share the screen?
Everyone, I'm Mai Renzhang from ThinkTime Group Limited with Model Team. Now I will introduce the top 1 solution for web with 260 million and inset with unconstrained track to watch large-scale mask face recognitions. There are our team members. We are from ThinkTime Group Limited with Model Team, and if you have any questions, please contact me by email. The training code and the model will be released very soon in GitHub. Here is the leaderboard, and we achieve excellent performance. We win the 2 championships of inset with unconstrained track and web with 260 million track. There are 4 main challenges for large-scale master face recognition. The first challenge is that large scale. The training set of web with 260 million is extremely large scale. How to deal with the large training image numbers and identities. The second challenge is web with 260 million is also collected from the internet. How to deal with the data noise. And the third challenge is how to trade off masked and unmasked recognitions. Adding more masked training recognitions will leading to a huge performance drop in unmasked face recognitions. How to balance. The final challenge is that CPU inference time is constrained to 1000 milliseconds. How to design a suitable backbone. For the large-scale face recognition training set web with 260 million, the 200 million identities introduce huge pressure to GPU memory, so mixed precision training is needed, and the distributed FC training is needed too. Even the most expensive GPU cannot afford the training for 2 million identities, so distributed FC connected is necessary for large-scale face recognitions. And there is a detail for distributed FC trainings. Even distributed FC may suffer from huge FC training problems, so partial FC training is introduced. Partial FC training can save much GPU memories and speed up much. Here are the results for distributed FC and partial FC. As we can see in the table, for the data noise, we do the same process in web with 260 million papers, and the performance gain is opted, as we can see in the table. For the trade-off for masked and unmasked recognition performance balance, we use the tool provided by GDAI-CV Zone to do masked augmentations and huge masked face recognition performance gain. we activate the Arduino tool with multi-processing CPU inference and reach 30,000 images per second rendering speed. There are some mask augmentation images, and we can see in the images the tool really achieve good performance. Simply improve the mask to augmentation ratio will lead to a performance drop in non-masked face recognitions, so we need to balance them carefully. In the end, we use the mask augmentation 15 to achieve a good balance. For the last challenge, CPU inference time constraint, since WebFace 260 minutes track limited the CPU inference time for 1000 milliseconds, and the inside phase unconstrained track limited the GPU inference time for 30 seconds, so a highly efficient CPU inference backbone is needed. We use the IDC-guided new agriculture search to get a multi-branch CPU-friendly backbone. As for the IDC-guided, we want the different branch of the model to be complementary with each other, so we minimize the KL divergences from different branch information flow. Here is the search space, and the IDC-guided search achieve excellent performance under the certain slopes constraint, as we can see in the table. High parameter tuning is also important for face recognitions, and the loss function, decay, and dropout are the most important high parameters we need to tune if we want to train a good model, as we can see in the table. The final part is fine-tuning to improve the mask face recognition performance. We also fine-tune the model trained with mask ratio 15 with the mask ratio of 33. As we can see in the table, huge mask face recognition performance gain can be achieved after fine-tuning process. And this is our final submission for WebFace 260 million track and the inside phase unconstrained track. We win the 2 championship. This is the end of my share, and thanks for your listening. If you have any questions, please contact me with my email. Thank you.
Let's move forward to the next presentation from Kakao.
Okay, so is Varian, can you hear me?
Yes, yes, I can hear you.
Okay, okay.
You share your screen.
So my presentation is available. I don't know how to share my presentation on this web.
There is a share screen in the bottom.
Share screen. Okay, got it.
Yeah. And so, then you can share.
Someone desktop 2. Change skills. Open. Should be able to record. Is my slide is on public?
No, not yet. Not yet.
Not yet.
When you screen, when you share the screen, you can select the app you want to share.
Yes, one more time. So, okay, here.
Okay, okay, nice.
Okay, great. So, first of all, I appreciate this invitation for presenting our works on these challenges. So I'm Eden, a member of this group at Kakao Enterprise. Here we will introduce our approach to mask face recognitions. So we would like to thanks to the organizers of these challenges and their huge effort for building training testing set. And first of all, here we introduce our big face paradigm, which is our big picture for improving the performance of the face recognition with masks. And so this challenge was a great chance to verify the effectiveness of our big face paradigm. Specifically, we believe that if there is no dataset bottleneck, big face recognition models can achieve a great performance improvement. So in this challenge, we verify that our model shows better and better performance improvements in both mask and standard face recognition as a function of the number of parameters. However, in most face recognition applications, it may be impossible to use such big models because of their huge amount of memory consumption and latencies. To tackle these limitations, we can adopt knowledge distillation for extracting informative knowledge from the big model into smaller models. The figure in the right shows our submission results. You can easily be aware of that as enlarging parameters of the CNN models, scores of MFR is getting better and better. So, in compliance with the FRU ITS 1000 protocol, we utilize the ResNet 240 for the final submission. And by using the knowledge distillation from our big model, we further improve the MFR scores. From now, we will explain a bit details of our approaches. First, we use two off-the-shelf mask face synthesized tools. The reason we use different tools simultaneously is that they show a bit different characteristics in their generated images. One thing we found was that we sampled masked augmented face images from the wet face dataset whose ratio of 0.35 rather than 0.5. And we observed that by this sampling ratio, we could roughly move our focus between masked and standard face recognition. Second, we will describe the architecture of our models. In the first round, we adopt a mixture of expert structures, but we observe that the plain ResNet counterpart shows a better performance than that of our MOE variant. So we employ the plain ResNet as our feature extraction network at the final round. This model is inspired by the ArcFace paper, and there is no bells and whistles on this model. Because we did not know the largest model acceptable under the FUT 1000 protocol, we gradually increased the trainer parameters of our model. Architecture parameters we used are listed in the table 1. Finally, ResNet 240 was employed in the final submission. Most batch normalization layers are removed manually before the submission. As our loss function, we used a convex combination of the cost space and angular distillation loss, whose margin, scale, and Lagrangian multiplier of 0.4, 64, and 9, respectively. We finished this challenge with the MFR score of 0.0769. When training our big face distill, we employ the data parallelism for the feature extraction network and model parallelism for the classification weights. When implementing the model parallelism, we adapt an idea from the partial FC, which allows to deal with 2 million identities in training. Other distributed training techniques, such as micro-batching, checkpoint, zero redundancy optimizers, LARS optimizers, and mixed precision were employed as needed. All models were trained on the PyTorch 1.8 framework, and 32 or 64 GPU cards were used per a single training sessions. Okay, it's the end of these presentations, and we still keep going on our research and plan to be published in the near future. Thank you for your attention, and feel free to contact me via email for further discussion. Thanks.
Okay, thanks for your presentation. There are several questions in the Zoom chat. Is there any question in the Zoom chat?
So, excuse me, room chat. Room chat that the hyperparameter is very related to the backbone, so you need to tune the hyperparameter with the models. Okay, so we have you tried the backbone other than ResNet? So we okay, first, why does dropout works? So the model you put million parameters, so dropout is needed. Okay. Okay, so the question is, John, the hyperparameter is very related to the backbone. So you need to tune the hyperparameter with the model.
Okay. If I also can't understand the meaning of this question. Okay, we can focus on how you try the backbones other than ResNet, any other backbone.
Yes, we try to. So actually, in the first round, we adapt a simple mixture of expert structure. That means we have multiple output layers as shown in this slide. So mask face feature layers and non-mask feature layers and classification layers. And these two features are combined with these masking scores, and final output will be used to the face classification rate. But we observe the plain ResNet shows a better performance than that of our MOE variant. And mostly our this backbone is a bit huge latencies compared with the simple ResNet. So we switches our backbone to plain ResNet.
Okay, I got it. So staking more ResNet blocks is more effective than change the structures. Yeah.
Yes. Yeah.
Okay. Thanks again for your presentation. And
thanks.
Okay, thank you. Let's move forward to the next talk. Because DeepCam has another complete talk, and so we move forward DeepCam's talk now. Hi, is DeepCam?
Yes.
Okay.
Yes, I'm here. Just give me 1 second.
Okay.
Okay, can you see my slides?
Yes, I can see your screen.
Okay, let me put the slideshow. Okay, everyone, my name is Weijun Tan, a supervisor of the DeepCam team, and here are my team members, Delong, Kangli, and others. So we are presenting the work, our solution for the mask face recognition and the standard mask and the standard face recognition. So I'm very glad to see others' work, particularly the Senstem work, sharing about their techniques, like searching in the like auto ML space, and also a lot of tricks how to speed up the training, since the data is huge in this challenge. So that's some new areas we want to explore. So here We do not, we basically use a standard network architecture. This is the ArcFace or the inside face architecture. Thanks a lot for your outstanding work. Due to the training time and our resource limitation, we do not explore like other networks we could, but we don't have enough resources. Anyway, here is our network architecture with all our innovations. So on next page. Okay, on this page, we list of the bag of tricks we used in our solution. First of all, ArcFace framework, and then we use balanced mask and standard data set. The third one is our own YOLO 5 face detector. We used it to replace the retina face on the test data for the face detection and landmark detection and face alignment. And we see that this brings some good performance improvement. And we have a STEM unit, drop block, and feature concatenation, and of course, training strategies, including data augmentation and learning rate strategy. Let me turn back here. So we have the YOLO 5 face detector on the test data. We have augmentation on the training data because training data is already cropped, face is already cropped. Then we have the new STEM unit to replace the, we introduced this new STEM unit in front of the ladder work to speed up the training speed. And we add this drop block to replace the, what's the name? The drop block. We used drop block to replace, okay, oh gosh, something I got stuck. The very commonly used technique to prevent the overfitting. So we add this in the last two layers of the rest block of the rest lab blocks. And then another technique we use is the feature concatenation. So the standard feature dimension is 512, but we can use like two models, and we concatenate the features of different backbone networks, and we find that also brings pretty good improvement. Okay, first the balanced data set. I just noticed that SenseTime studied the same way as we did, and they studied like 10%, 20%, and 15%. They found 15% gave the best results, and we have a similar observation here, but we did not keep the record of our experiment results. So maybe 10% is best or 15% is best, but we used our 10% in our experiment. And we generate a masked data set using the tool FMA3D. We noticed this trend very early in our study. So when we use like a larger percentage of masked data set, then the performance is biased to the mask face recognition. Other way, is biased to the standard face recognition. I think that's why the organizer of this challenge changed the metric to include both the mask face recognition and the standard face recognition. Okay, a little bit results on our YOLO 5 face detector. So this is based on the YOLO 5 object detector, but we add quite some new stuff into it, including a STEM unit to replace the focus layer. We use a smaller kernels SPP, and we add P6 block and landmark block. Right now, the YOLO 5 has the P6 as a standard, but when we started our work, P6 did not exist yet. I'm not sure if YOLO 5 was inspired by our work to introduce the P6 as a standard block in their current version. Okay, more details can be found in our archive paper. And this is the benchmark of the YOLO 5 detector on the wider face. So we have quite some different models, different sizes models, from very large to very small and to tiny models. So in our this challenge, we use our medium model due to the limit of the inference time. And this YOLO 5 face detector is open source. Some example of the landmark of the retina face and the YOLO 5 face. In the retina face is used as a standard face detector on this challenge. But if you look at particularly for those faces with large poles, if you look at it very carefully, you will see that the landmark, the estimated landmark of our face detector is actually better. And this will be benchmarked in face recognition results when we use like two exactly same model, but to just replace the face detector. Okay, STEM unit, I will skip this page due to the time limit. So we have a STEM unit, but later on we find that the ROSLET D works better. So we changed that in the second phase. A little bit about the learning rate strategy. We use the cycle cosine learning rate strategy, and with warm up of 0.1, and then this learning rate reduces according to the cycle cosine learning rate. So in our study, we first study every component of the network on the smaller Glint 360K dataset. We do some ablation study, like we do this, we add this different components incrementally from the baseline, and we just watch, how does every trick works on this small data set. So you see, we have the baseline, we plus the cycle cosine learning rate and data augmentation, like a random shift or random noise, and then STEM unit, and this SE and drop log and EMA. We see that this performance keeps increasing gradually, and so after we optimize, after we have like a good combination of all the components, then we change this, we move to the web face track, and we retrain the model and test it on the web face track test data. So this is, then after that, we explore the concatenation of different backbones. So back on this page, we use a small backbone like a ROSLET 34. And then on here, onto the web face, we use, we try different backbones like larger backbone, R50, R100, or R124, all the way to R200. Since we use the concatenation of two backbones, so we have to worry about the inference time, the training time, and the inference time. So when we use this concatenation of very large models, there are a few other additional tricks we use. For example, we can freeze the some beginning layers of R152 and only train the new added layers to save the training time. And if the inference time is over limit of 1 second, then we can just dig into all the weights. And when the weight is very small, for example, less than 1e-6 or 1e-8, and then we just manually force all those weights to 0. That way we can save the inference time and to meet the constraint of 1 second. Okay, so first let's look at the results. The first two lines, if you compare the two first lines, the backbone and the concatenation are exactly the same. The only difference is we replace the retina face with our YOLO 5S. This is a small model. So, and the training data set means the data set we use to train the data detector. So in the first two lines, we see by simply replacing the face detector, we improve the FMMR from 0.1065 to 0.1060. So this is this is some improvement. And by the way, so we have our small detector here. If we use a larger one, then the performance will be improved further. So another improvement on the face detection is that we noticed that in the wider face, there are very few large face, but in the web face data set, there are some pretty large faces. So then, by noticing that, we obtain some large faces from the multi-task facial data set. And we retrain our face detector so that it can detect large face better. And another improvement is since there are a lot of masked faces, but the standard face detector does not detect, is not trained on the masked faces, even though it can detect them pretty well. So we add some masked faces by the data augmentation, and we add that to the training set for the face detector. And we also noticed that by this trick, the performance can be also improved, like from here to here. Okay, and then after that, after all that study, we moved to use larger backbones. Like here, we use the concatenation of RASnet 124 and 152, and also further 152 and R200 with all the tricks I just talk about, how to save the training time or how to save the inference time. And our best results is 0.0923, even though our submitted best results is 0.0925. Okay. Our final benchmark results in this web face track, our all mask FFR is 0.025. That's not our best. Our best is 0.0923. Anyway, that's our best submitted result. And in this standard face recognition results, we achieve 0.0163, which is rank number 3. Okay, and then on the inside face track, unconstrained subtrack, this is our performance, and we are ranked number 5. We also rank number 5 in the Glint 360K subset, but I did not put it in here. Okay, that's all our presentation, and thank you for watching. If you have any question, you can ask now, or later you can email us. I did not put the email here, but you can find it in our paper. Okay. Any questions?
Thanks for your report. And there is one question in the Zoom chat. Does the multitask dataset contains bounding box and landmark one choices?
It has the bounding box, and it has also the landmark. Yes.
Okay. Which dataset are you using here? Which multi-dataset? Multitask data. So you have the weather face, which is released by Retina Face. We have landmarks and 5 landmarks and a box. Which dataset? 47. Which one?
Yeah, 47. You can look at the reference 47 of the paper. It has all the detail. Yeah.
Okay, no problem. No problem. Thanks for your improvement on the whole system, including the detection part and the recognition part. Thank you.
Yeah. By the way, since all the other team they use the default Retina face detector, I believe if they replace the face detector with our face detector on top of what they already have, the performance may be improved further. Okay.
Okay. Thanks for your sharing this new face detector yellow V5 face. Okay. Thank you. Okay. Let's move forward to the next talk from SenseTime. They also achieved the first place in the deep Jilin track. Yeah.
Excuse me, can you hear my voice and see the?
Yes.
Yes, I can see
Okay.
your.
Okay, let's begin. Hello, everyone. I'm Bing Qi, a computer vision researcher from the base model team of System Group Limited. Please allow me to thank the competition organizers on behalf of our team members. Today, I'm here to share our solution for the inside-phase GLAN track. There are 6 researchers in our team. Each of them does great contribution to our final solution. If you have any questions after this workshop, please contact me with the email address. Okay, let's begin. I give a roadmap of the results breakdown along the computation process. Based on the 100-layer ResNet, we first introduced the hard archiface loss. Considering this is a mask face recognition computation, we also adopt data augmentation, including random flip, random arrays on sunglass and hat, and mask augmentation. The model is limited by the inference latency on GPU, so the reparameter strategy will be a good choice. After fixing the training setting, we scale up the res 100 to meet the latency requirement. To further boost the performance, we ensemble multiple teacher models and distill the knowledge to student model. This is the performance roadmap, and the performance is the weighted sum of mask and all. Okay, for more detail. Here I show the formulation of hard archiface loss. It is similar to the origin archiface, but we decouple the positive scale and the negative scale. In the original archiface setting, the positive scale and the negative scale is both set as 64, but in our experiment, we set the positive scale with 64 and the negative scale with 80. We find this can dramatically boost up our model's performance. As for the augmentation, we focus on the mask. We adopt the PhysX tool to add mask on images, and this is a pipeline. In our experiments, we change the ratio of mask data in the training data set. It can be observed that the performance will increase at first and then drop at the mask ratio increasing. Another interesting observation is that if we keep increase the mask ratio, the performance of mask will also drop. In the future, in the further ensemble teacher training, we train teachers with different mask ratio and ensemble it to achieve ensemble teacher with both good performance on mask and common setting. As for the model architecture design, we design model based on ResNet 100. The reparameter strategy will bring extra training parameters and flops, but will not do harm to the inference latency. Also, there is another trick. We can find that the batch norm layer is a nonlinear layer when training, but it is a linear layer when inference. So we can merge its parameters into the previous con layer, and you can reduce the model's inference latency. At the same time, attention models such as SENet is also time consuming. We tackle the lightweight formulation, ECANet for channel attention. There is also an interesting observation. The previous paper, diverse branch block, it is a more powerful operator than ECANet, and the paper showed that DBB have better performance. But however, when we introduce the channel attention model into it, something changed. We can observe from the table, if we use channel attention, as for the basic block, there are 2, 3, 3 convolution. If we add the reparameter to both con, the performance is bad. But if we only add the reparameter on the first block, it will bring a performance boost. Also, the diverse branch block is marginally better than ECANet. This is an interesting observation, and maybe it's worth considering. Okay. We also propose a NAS-guided teacher architecture design, and the work is this is my paper, and it is in submission. In the future, I will put it on the archive and release related model. Neural architecture search guided teacher architecture design is the core technology in our method. Neural architecture search can help to search for the efficient architectures given the search space. Revisiting previous multipass architecture, we find that the operators tends to be diverse. Then we introduce information diversity. Given an n-pass architecture, we hope to minimize the KL divergence between ICE pass and other information streams. This can be formulated as the above IDC. Okay. Then we add information diversity into the reward function of deep reinforcement learning-based neural architecture search algorithm, jointly optimize the performance on proxy task, computation budget, and the information diversity. In the figure, we compare the architecture when searching with and without information diversity. It indicates the effectiveness of information diversity guided search algorithm. And if you have further questions about our work, okay, you can ask, and also you can email me. For the last section, I will introduce the model example mimicking. Experiments show that in the area of face recognition, the performance tends to be continuously increasing if you train large model. Of course, there should be enough data or it will be overfitting. In this competition, we use multiple architectures with 0.3 billion parameters and 1 billion parameters as teacher models. Given the large parameter number and flops, we use tricks including mixed precision training, checkpoint, and zero to train them on NVIDIA A100 GPU with 40 GB GPU memory. Now we have teacher models with high performance. We need to consider the knowledge distillation. Given the strong augmentation, it is important to keep the consistency between the teacher's feature and student feature. We should keep the student model and teacher model in GPUs at the same time. You should both inference and to extract the feature. For model example mimicking, we need to concat the embedding of different teachers and use the L2 loss function. However, L2 loss function can just guide the student to a similar space with the teacher models. It is essential to add extra recognition tasks. So you can see the picture. There are two loss, embedding loss and arcface loss. However, by analyzing the gradient, we can find that during the training process, the gradient of L2 loss and arcface will conflict in some case. So we propose a multi-stage distillation method to decouple the knowledge distillation and the recognition task. In each stage, we choose the cosine learning rate to train it. At the same time, we also tackle the online hard example mining strategy. Extra hard examples will help to fulfill the input space and bring significant performance boosting. And we will release our detailed technical report in this month. Okay, this is my talk. If you have any questions, please don't hesitate to ask me. Thank you.
Okay, thanks for your report. Is there any question? Okay, how about the accuracy if we remove the channel attention?
The channel attention model will bring about 1.5 accuracy in the GLAND track, and there is something strange between the relationship between the parameter and channel attention. If you use SENet and ACNet, the performance will not so good. But if you use ECANet, it will co-work with the parameter model. This is interesting observation.
Okay. Thank you. Yeah. Another question: why we need a cosine learning rate schedule in training?
We believe that it is impossible for the knowledge distillation process to be overfitting, so we can train as long as we can. But at this time, step learning rate do harm. Step learning rate performs not so better than cosine learning rate. For example, in the ImageNet setting, when people train for 3,000 epochs, they always use cosine learning rate. But if they train for 100, they commonly use that.
Okay. Thank you.
How many?
How many teachers do you use?
In the GLAN track, we mainly use 3 teachers, but this is a cascaded distillation process. We will ensemble and retrain, so it's hard to count.
Okay. Thanks again for your talk. Last question. How do you guarantee the IR architecture search will converge on GIS?
During the search process, we will plot the reward we will plot the reward. If we observe that the reward value keep increasing and tend to converge, we will think that the nets will be converged. And during the process, we also sample some architecture from the space and retrain them to compare it with the baseline model. And if we observe that the retrained model's performance is still growing, and we think that it will really converge.
Okay, another 2 questions and the last 2 questions. Okay, so is there any ablation study on balancing architecture loss and L2 loss?
Yes, we will release it in our detailed technical report.
Okay. Did you directly search your architecture on the WebFest dataset?
Oh, this is the GLAN track. So I search the model only use the GLAN data, or it's due to the rule.
Okay, got it. Did you try parameter average?
Parameter average. I don't get. I don't know what it means. But okay. But the EMA will works, but about the 0.1 performance boosting or no, I'm not sure.
Okay. Thanks for your report. Let's move forward to the next report from Alibaba.
Thank you.
Okay. Sorry. Okay.
Can you hear me?
Yes. Sorry. I muted you.
Okay. Okay. Let's start.
Yes.
Hello, everyone. I'm Meng Wang from Machine Intelligence Lab of Damo Alibaba Group. Today, I'm honored to represent my team, MindFT, to give a talk about our solution towards most robust face recognition, which achieved 1 champion and 3 runners-ups in the ICCV 2021 mask face recognition challenge. In this challenge, there are 3 kinds of training dataset. MS1M is a relatively small dataset. Glean 360K is a medium dataset, and Whiteface 40M is a large one. Then there are 2 kinds of taste dataset that are separately distributed in inside face and Whiteface track. The taste dataset in inside face track contains mask and standard face images from different races, while face images from Whiteface track came from real scenario. It's worth noting that the number of positive and negative pairs are enormous. Then the evaluation metrics are listed on the table. Note that there are not only performance evaluation metrics, but also featureless and inference time constraint metrics.
From this slide, I will introduce our solution in this challenge. Firstly, let us start from the data. As we all know, the less noise of the training data, the better performance of the trained model. So we propose a self-learning based data cleaning pipeline. At first, an initial model is trained using the original training data. Then this model is used to clean the noise within the training data. The cleaning process contains ID union, inter-ID cleaning, and intra-ID cleaning. For each ID, we use dbScan cluster algorithm to calculate the center feature. Then we use the center feature to perform similarity search. The high-dimensional vector searching engine is Proxima, which is proposed by Alibaba Damo Academy. Then we perform self-learning by initialize the ICE model as the I+1 model. Note that we first perform inter-ID cleaning, then intra-ID cleaning, which is different from CAST. Our schema has good robustness as the center feature are updated after the inter-clean process. Then we generate mask training data online using the mask-to-face image blending approach, which is the same as the previous teams. This approach is adopted from FaceXZoo. We randomly select one mask style from 8 mask images to generate a mask face image. Several examples can be seen from this slide. Then we use NOS approach to search a high quality backbone. A zero-shot NOS or ZenNOS proposed by Alibaba Damo Academy is used in our solution. ZenNOS uses Z-score instead of an accuracy predictor to rank the search architectures. Note that the Z-score is positively correlates with the model accuracy, while the calculation is much faster than traditional NOS approaches, as it doesn't need train the network parameters. Specifically, our base model is IRSE 100. Then the number of channels in the input layer, the number of channels in the block layer, and the number of units in the whole backbone are searched through the NOS. Then the loss function, the curricular loss is first proposed by Tencent, which can perform training from easy to hard examples, while the training data usually has an extreme unbalanced distribution, as shown on the right side of this slide. In order to solve the long tail problem, we propose a new loss function named balance curricular loss, which merges the balance softmax into the... Sorry? Okay, let's continue.
I interrupted you, sorry. I just muted the noise, yeah, okay.
Okay, no problem. Let's continue. So we propose a new loss function named balance curricular loss, which merges the balance softmax into the curricular loss. We found that the proposed balance curricular loss can improve the performance by more than 1% when compared to the original curricular loss. As we know, all the tracks of this challenge have inference time constraints. So knowledge distillation has the ability to train a small student model from a relative big teacher model. So we use knowledge distillation on the MS1M track. The total loss can be formulated as the weighted combined loss, which contains the balanced curricular loss and the distillation loss, that is L2 loss. Besides the approaches mentioned above, other tricks are utilized as well. Several data argumentations such as color jitter, horizontal flip, and cutout strategy are used. Label smoothing is also used to give a soft label instead of the hard one. Furthermore, Kasai learning rate with restart training strategy can produce better results when compared to the steep learning rate strategy. Final results of our team are listed in the table. Note that we've achieved first place on the wave phase ACFR track and third place on the main track. For the inside phase track, we have achieved second place on unconstrained track and third place on MS1M track. We can't do all the above achievements without the contributions from our team members. They are Liang Pengxu, Tao Fo, Yongfei Zhao, Mingqian Tang from Alibaba Demo Academy, Kai Wang, Jian Zhao, and Yang Yu from National University of Singapore, Jianfei Yang from Nanyang Technology University. Finally, I would like to introduce where are we from. We came from the Multimedia Intelligent Understanding Group of Machine Learning Intelligence Lab of DAMO. Our research scope include video tag, video search, video generation, video cover, and video sensor. We have achieved 7 champions, 2 runners-up, and other certifications from both academia and industry. More the details can be found in our Exploration Center on Alibaba Cloud. Welcome to join us. Many thanks to your attention.
Okay, thank you. Thanks for your report. And let me check the questions from the Zoom chat. Does cutoff augmentation really work?
Yes, because we use the curricular loss. So in the initial training from scratch, cutout is not useful. But when we get an initial model and then we fine tune with cutout, then the performance is can be increased. Yeah.
Okay. What about the level smooth? Another question.
We found level smooth can lightly increase the performance when compared to the hard label, but it's not the it cannot dramatically improve the performance.
Okay. Okay. Is there any question? Is there any other question? Okay, let's move forward to the last talk from Microsoft Research Asia. Yeah.
Hello. Hello.
Hello. Yes, I can hear you.
Okay.
You share your
Okay,
screen.
I'm sharing my screen.
Okay.
Okay, can you see my screen?
Yes, yes.
Okay. Hello, it's my honor to give my talk to share my experience on the Glint track. I'm Xu from Microsoft Research Asia. I face human team, and our team includes 3 members, including Chong, Yao Yao, and me. And my talk includes 2 parts about our training model structure and mask improvement. Because it's about the Glint track, we use the HRNet W64 to be our backbone and the high resolution net. And we choose a new loss function, the circle loss, with a gamma of 256 and a margin of 0.28 to replace the M softmax loss. And about the batch size, we use 32 GPUs on a mini batch of 32 that is a batch size of 1024. And about the learning rate, we use a polynomial decay and use a linear warm-up of 5 epochs. And also we applied a very big dropout rate on the back of the backbone. And using these high parameters, we got a good result on the non-mask phase result. But this model doesn't have a very good accuracy on the mask and result because this model never sees any mask photos. So we use apply some new methods to just improve the mask accuracy and while maintain the non-mask accuracy. And about About the data augmentation, we use the default mask augmentation pipeline provided by this challenge on the inside face. And we applied 2 downsampling head to separately deal with mask and non-mask input faces. I put a photo here. Also, we applied a mask classifier input from the backbone's output, the big feature, to classify whether this input photo has mask or not. If it has mask, we'll use the left downsample head to downsample this feature to get the final feature. And if no, we use the original downsampling head. And about the right downsampling head, we use the original training pipeline. We got this one. And this one on the non-mask is very good. About the left one, we applied 2 loss functions, 2 circle loss functions, which is to optimize the distance between the mask face feature and its root non-mask face feature. And another loss is between the mask face feature to this person's weight features. Because we find that separately use any feature or any loss to train this left and downsample head, it will get overfit, and the final test accuracy is not will drop. So with these 2 features, we find we maintain the non-mask accuracy and raise the mask accuracy significantly. And this is our final model structure. And let's see the sharing of my the green track. It's a little bit short. Do you have any questions?
Okay, thanks for your report. Is there any question? Okay, let me check the Zoom chat. What is the advantage of HRNet over ResNet?
We think that the HRNet has a very big feature map, maintaining from the bottom to the from the top to the bottom, and we found replacing ResNet. Even we found that this HRNet is even better than the DenseNet, and the accuracy is better.
Okay. What's the accuracy of mask classification?
We trained on the augmentation data, and we have a verification data set. And on the training, it's got 99%. On the verification, we have 5,000 people and 2 photos, and the accuracy got more than 99%.
Okay. Should the ratio of mask face in the training data be great enough to optimize the mask head well?
This is a kind of trade-off. We also tried several things like the other groups used. We replaced the training data about 10% to mask data, and after training this, we find the final mask will get better. But because the backbone sees some mask data, the non-mask accuracy will drop, because our challenge is the non-mask has more ratio and more important. And this after the trading off, we find that if the backbone never sees a mask, also gets better result.
Okay, thank you. Last question: what loss of mask and non-mask branch?
Oh, it's a very standard cross entropy loss.
Okay.
And 2 labels.
Okay. Yeah. Another 2 questions. Have you done ablation study without using the 2 different nets head for mask and non-mask?
Without using you mean you use only one head? Of course, using one head, the mask is about 4%, 4 to 5% lower. It's very low.
Yeah, I also understand this question. Yeah, okay. How to optimize the distance between mask feature and non-mask feature?
Oh yeah, now I said before that we use two circle laws, and one is very like the arc face, using this non-mask using this mask feature to the this person's weight feature to be the match pair, and another circle law is that we replace its weight, the person's weight with its non-mask face feature, that photos feature, and calculate the circle loss again. And this is the two losses to optimize.
Okay. Okay. So let's move forward to the next step, next part. We select two papers to do the presentation in our workshop, each one around 10 minutes. One is rectifying the data bias in knowledge distillation, and another one is boosting fairness for masked face recognition. Yeah. So are you there?
Hi, can you hear me?
Okay. Could you share the screen?
Okay. Yeah, I want to share my screen. Have you seen the PowerPoint?
Yes.
Okay. Hi, everyone. My name is Bo Xiang. I am a PhD student at ICCV China. It's an honor to present our paper, rectifying the data bias in knowledge distillation. This work was done when I was an intern at Time Research, working with Shenghan, Guanglu Accelerator. In this paper, we focus on the issue of data bias in knowledge distillation for representation learning. The growing scale of dataset for representation learning brings about remarkable improvement of performance, but also introduces data bias. For example, the popular dataset MS1,000,000-3 for face recognition demonstrates skewed distribution of data. Also, we find that most of the images contain frontal faces and are easy to recognize, while hard samples are few. We further quantitatively show the influence of data bias in knowledge distillation. By treating both the student and teacher models as mappings from image into feature, we found that the student fits the teacher's output well in the subspace containing many input samples, but poorly in the subspace where few samples appear. However, with more uniform data, the student can benefit from bias in rectifying and approximate the mapping of teacher better across the whole input space. To take a step forward, we quantitatively define the uniformity of a dataset. With features of images extracted by the teacher model, we first define the distance between images as the distance between features. Then, we estimate the continuous probability density for each image through kernel density estimation, a non-parametric estimation method in statistics. Finally, we define the uniformity as the entropy of density distribution for the training set. After that, we introduce two novel methods to improve the uniformity so as to improve the distillation performance. The first one is called extrinsic sampling. Specifically, we first uniformly and randomly sample a vector in the teacher's output place. Then we select the image whose feature is the nearest to this vector. By repeating this process, we can generate the list of training samples, which is expected to be more uniform in the embedding space. Extrinsic sampling is simple and parameter-free, but may fail in some cases. Then let us introduce the second method, intrinsic sampling. We are motivated by that the training data with greater density should be sampled less. So we set the sample probability of training data inversely proportional to the estimated density. Moreover, we compare the uniformity of original datasets to the resampled ones by our methods, and we see significant improvement of the uniformity. We conduct experiments on face recognition and person identification to evaluate the proposed methods. For face recognition, our methods can surpass naive knowledge distillation with a significant margin compared with the improvement brought by the knowledge distillation. Also, similar trends can be found in person identification task. We further compare our methods with the state-of-the-art, including sampling ones and reweighting ones. We find these methods show little help under our setting, and the proposed methods can outperform them significantly. We also try training students without the distillation loss. Compared with naive knowledge distillation, we find similar performance can be achieved by only resampling the data. We speculate some knowledge is transferred to the student via data distribution. Last, we show some visualization of the resampled data. It can be seen that hard images, for example, with large pulses, are sampled more times. Also, the number of images per identity becomes more balanced. In conclusion, we introduce uniformity as a unified view towards the bias issue and provide a quantitatively defined definition of uniformity. We further propose two uniformity-oriented sampling methods, extrinsic sampling and intrinsic sampling, to generate more uniform training data. Extensive experiments are conducted on large-scale face recognition and person re-identification to verify the effectiveness of the proposed methods. Thank you for your attention. Okay, are there any questions?
Okay, thanks for your report. Is there any question to this paper? Okay, no questions by now. Okay, because it is very late in China, let's move forward to the last paper report. And,
thank you again.
As soon as possible. Thank you. Thank you.
Can you hear me? Wait.
Yes.
Okay. Yeah. Okay. Can you hear? I'm Star.
Yes, yes.
Okay. Hello, everyone. My name is Xin Longhao. I'm a master's student in University of Science and Technology of China. Today, I will introduce face recognition. Members of this work come from University of Science and Technology of China. Members of this work come. This method comes first in masked face recognition challenge. I will introduce our work from 4 parts. In the first part, I will do the introduction of this work. Then in the second part, I will introduce our method. Then I will show experiments and results. Finally, I would make a conclusion on this work. Face recognition achieved great performance in recent years, but there is offense too. For example, a face recognition system recognizes one black person as another black person, and the probability of this situation is different among different ethnic groups. It's awful. So we need to consider fairness when designing a face recognition system. But most of face recognition systems are awful. For instance, the recognition results of lighter persons are better than the recognition results of darker persons. And the recognition results of male are always better than female. It's harmful to fairness. Besides, there is big racial bias in deep face recognition systems. Table 2 shows recognition results of different ethnic groups, such as Caucasian, Indian, Asian, African. The recognition results of Caucasus are always better than recognition results of other ethnic groups. And the deep learning model is data-driven, so the distribution of face data sets would affect the recognition results of different ethnic groups. In table 3, we compare the distribution of different face data sets and find most face data sets are imbalanced. It will cause bias in face recognition. And we also show racial compositions in face data sets. According to study, we can make a conclusion. If we want to get a fair face recognition system, we need to reduce the bias of the data distribution. During the epidemic situation, masked face recognition is becoming a hot topic, but also bring new challenge for fair face recognition. For instance, the voice and noise are important to recognize face of Asian group. Masks would further reduce the recognition rate of Asian face. It would bring fairness in face recognition system. So to this end, we try to boost fairness for masked face recognition. For increasing the recognition results of masked face, some papers combined the VGG2 dataset with augmented masked face and train the model following the original pipeline described in FaceNet. Besides, some papers use multitask learning to separate ethnic identities. It's helpful to get fair results. And it's an overview of our method. When using the original dataset to train a masked face recognition model, there would be a fairness between different ethnic groups. And using masked enhancement, data balance, and asymmetric arc loss, our method obtained a fair and better masked face recognition results. For training data, the dataset is created by inside face, recalling the original dataset to obtain a better dataset. For test dataset mainly contains masked face and general face. For evolution metric, it mainly uses TAR and FAR. And the TAR of mask set and bias between ethnic groups are important. To this competition, mask face is very challenging, and the distribution of training data is very imbalanced. And the biggest problem is we need to decrease bias and increase accuracy of mask face at the same time. The proposed approach consists of 3 parts. They are mask augmentation, face pre-process, train model, and inference model. Inside face presents a tool for masking face in images. We show some face images without mask is in the left, and with the mask is in the right. And we use the resampling method for the original trained dataset, but for masked data, there is something different. The noise and noise are more important to recognize the face for Asian than other ethnic groups. So the mask would reduce the recognition rate of Asian more. We mainly increase the weight of Asian based on data balance. For data enhancement, in train stage, we use many enhanced methods to improve data diversity. In test state, test time augmentation is used to get a robust feature. We put the original face and the face which is flipped horizontally into back Y. And then both of output future vectors would be added together to produce final future vectors. To train model, we mainly use structure or arcface. For model loss, we propose asymmetric arc loss for training. It contains arcface loss and circle loss. We can make a combination for these two loss to use both of their advantages. Besides, the fork loss is used to balance the positive and negative simply. In inference model, the final prediction is obtained by calculating the cosine similarity between two future vectors. Next, I will introduce experiments and results. We set the sampling rate and mask color probability manually. Besides, in the tree stage, image is taken from masked dataset with lambda. We choose lambda equal to 20% for our final choice by ablation study. Okay, in this work, we do ablation study to validate our ideas and find the best system. When the lambda increase, TR of mask phase would increase, but the TR of all phase would decrease. We test the effect and find 20% is best. Then we compare the result of original sampling method and our sampling method. Our method considers the impact of masks or fairness, and table 6 shows that our resampling method is effective. And table 7 shows information of different model combinations. It shows that the model in our method are all helpful. Some computation results of Microsoft Cerebral 1 million track are shown in the table 8. Our team finally got great mask score at a lower bias compared with the other top contestants. To further validate our approach, the method is also tested in Berlin track, and we also get a great score. Finally, I would make a conclusion. This paper proposes a face recognition system with fineness and robustness. And the highlights are the combination of mask argumentation method, the data sampling approach, and the symmetric arc loss. And this paper obtained fair face recognition results and better results on mask face. Okay, thank you. Thank you for your list.
Okay, thank you. Thanks for your report. Is there any question regarding this paper? Okay, it looks no question. Let's move forward to the next step. Okay. So let's move forward to the last part. Thanks for the workshop sponsors, OneFlow and QV Technology, Zolo, and Export AI. Thanks for the funding donation. And we have different tracks, and for different track we have the hard copy of the certificate. Please contact Guojia for the certificate of the incentive track, and also he will contact you to allocate the award, the funding award to you. And please contact with Zhu Zheng for the workplace track for the certificate as well as the funding. And in addition, we give 2 best paper award. One is rectifying the data bias in knowledge distillation, and another one is best workshop paper run-up for boosting fairness for mask face recognition. And in our challenge, we know that knowledge distillation is a very important tricks to improve the performance, and fairness is a very important and timely research topic, and we wish the community can put more attention, put more focus to these topics. Thanks for your support today, and thanks for everybody to listen the take part in the workshop for almost 5 hours, and thanks for everyone. That's all for today's workshop.